All right, so if you do a little bit of downloading in the background, by the time we get to the first live exercise, then you can get going with us. And let's see, let's point this a little differently so you can see the whole thing.
Thank you, I should have done that.
It's hard to tell before we have something to show, yes. Okay, so welcome once again. Yes, welcome from our SASyLF. This is art by Rob Simmons, who collaborated. He explained the theory of 12 to me, so I could implement SASyLF on top of it, which was very cool. Okay, so what's the motivation for this tutorial? Well, teaching programming language theory and proofs is hard, right? It's a lot of fun, actually, I think, and it's very rewarding, but it can also be challenging. And I think mathematical proofs in general are difficult, right? There's a lot of details. It's very easy to get them wrong. I think the discipline of kind of thinking in a rigorous mathematical way is maybe not natural to many students. I think for some of us it is, and maybe that's why we gravitated to this field, but it isn't for everyone. And so you have to learn that, and it is possible to learn it. But it's challenging, and I think one of the things that happens with homework sometimes is we give a homework and students get these details wrong and the proof is wrong, and we give them feedback, but it comes too late, right? If we're lucky, they come to office hours and we can work with them right then. But if they don't, then maybe they only get the feedback when they've turned in their homework and they get it back graded a few days later, and now a learning opportunity has kind of been missed, right? If the student goes back and they kind of try to redo it without the mistakes, then maybe they can learn, but often that doesn't happen, right? And so the best place to intervene is in the feedback loop as the student is writing their proofs. And so we want to help them by having a proof assistant. It seems like a natural thing, right? The proof assistant is rigorous. You can check whether the details of the proof are correct. It can provide immediate feedback. So the student knows when they've got something wrong and when they've got something right. Students really like the fact that, when the tool says it's okay, that the proof really is okay, right? That's super rewarding. And when it's wrong, maybe that's a little frustrating, but then they know they have to do something, right? And it drives them to get that satisfaction from, oh, I've finished this assignment, right? And it can actually help encourage interaction with the TAs and the professor. They come to your office hours because they know something's wrong. And now you have a teaching opportunity. So I think it's really potentially very beneficial. In the long term, I think proof assistants can raise productivity. I don't know if that happens in the immediate classroom, but I think in terms of learning productivity, it definitely can. One thing that we maybe is not on the slide, but I think is valuable, is that I feel like when I implemented SASyLF, then that's when I really understood what a proof was, right? And okay, not everyone's going to implement SASyLF. Maybe that should be an assignment someday. But I think just by using a tool and understand, you get to understand what that framework is, and you get to understand, the nature of a logical proof, right? And the idea is this Hindley-Milner correspondence, the proofs are actually programs under the hood, right? And I think if you get students a sense for that, then even when they go outside the tool, and they write a proof, in a paper or on an exam, it's not checked. They understand what a proof is, and they can make that logical argument even outside the context. And we've certainly seen that in our classes, that it does transfer from the tool to the page. So I think just like good compilers make and interpreters and so on make programming more accessible, good tools can make proofs more accessible. And there is a big state of the art in terms of educational tools. Here are a few that have been available for a number of years. There's probably even more today that I may not have put on the slide, that are focused on certain domains of theorem proving. Things like let's do number theory, let's do linear algebra, let's do geometry, and they're very focused on education. But there isn't something that's comparably education focused specifically for programming language theory. That's what we set out to build with this in mind. Now, there are, of course, a lot of proof assistants used in programming languages. So I've listed a bunch of them here. And I saw somehow I left Lean out for the slide. but that's probably not the only one that isn't even here. But there's a lot of these proof assistants that are very highly expressive. They provide great automation. I think for expert users, they can actually enhance your productivity, and they certainly enhance like our confidence that a proof is correct. But the drawbacks is it's a steep learning curve, right? And part of that's the tool notation, which can be unfriendly at first. Part of it's maybe even more encoding techniques, right? How do we express a variable? Well, a variable is an integer, and the integer shows how many layers of scope from where the variable is declared. And when you do substitution, you have to manipulate these integers, right? It's all actually quite complicated. And I guess it's relevant to programming languages, but maybe not necessarily to the specific things you're trying to teach in your course, depending on what your focus is. And so time spent teaching the tool is time not spent teaching programming language theory. And so as a result, most programming language courses that I'm aware of, even if they teach theory, they don't use proof assistants. Some do, but probably most don't, and maybe especially at the undergraduate level. So we'd like to see if we could change that. So SASyLF is a tool. We'll be talking about the tool, but also kind of the pedagogy and how we use it to teach. It's intended to be expressive and sound, so it's based on the same meta theory as 12. And I had an undergraduate thesis student who actually developed that correspondence. And we found it can improve a wide range of properties. So some citations coming later on. But almost everything in TAPL can be formalized and improved in SASyLF. Basically everything except for technical reasons, relational arguments. So it's supposed to be easy to learn. We have a proof syntax that's just like what you write on paper. And kind of a minimal required math background, just inference rules and induction, which you probably want to teach if you're teaching programming language semantics anyway. We want to match programming language theory needs, so supporting variable binding, so people don't have to do encodings and alpha equivalents. That's all built in. Explicit notation, so every step is specified completely. This is important for people learning proofs, right? So they can read the proofs and follow along the logic. They can understand where they are and what they know. They can write down their goals. So these things are, the notation is more explicit than existing tools, and that can actually slow you down if you're trying to write a professional proof. But for early users, it's really, I think, quite ideal. Rapid feedback, so automated checker like other proof assistants, and support for partial proofs. So you can say, by unproved anywhere, and it just leaves you alone. But there's a little marker that says, oh, here's something you should finish before the proof is done. And then good error messages, right? So we want to purely local checking. We want to pinpoint the location of the error, and we want to tell you the error in terms that you can understand. So I think SASyLF mostly achieves these goals. I think we could be better in a few areas, and we're continuing to try to improve it, but that's our design goals for the tool. So why should you stick around for the rest of this tutorial? Maybe you're thinking about teaching with a proof assistant, but you worry about the cost. So we have used SASyLF successfully at CMU, U Wisconsin, Milwaukee, UCLA, Northeastern, perhaps some other schools. We've done some surveys. The details are available on the SASyLF webpage, but students like it. They think it's fast to pick up, and they think it helps them learn more effectively. So we're going to introduce you to how we teach with the tool, provide pointers to the curricular materials, that's what you've downloaded, and hopefully give you what you need, at least part of what you need to make an informed decision about teaching. Maybe you just want to learn about formalizing programming language with proof assistants. So SASyLF is certainly not the most widely used one, but in some ways it might be the easiest to get started with, and it's powerful enough to prove many publishable results, so you can actually go places with it. And it's also, a starting point, right? So we'll talk about ways to transition to other proof assistants, but the service syntax of SASyLF is pretty different. Probably every tool has pretty different service syntax, but underneath, the same principles apply, right? So I think if you learn those principles in any tool, it'll be easier to learn other ones as well for you and your students. So here are our goals. We're going to discuss some pedagogy, share our experience from the courses, share their curricula we use to teach PL theory, introduce SASyLF, and give you some hands-on experience. All right, and that's basically the outline. So we're mostly at the end of 15 minutes, but I wanted to have a little discussion in this area. And then we'll talk about how we introduce proofs to students using proof assistants, both in our classes, and then we'll do a live demo and a hands-on exercise. And then we'll extend to how to model operational semantics and proofs about it in a programming language. So this is kind of like proofs. This is proofs about operational semantics. This is proofs about typing here. And this gets interesting because, well, here we see some of the support for variables that's built into SASyLF. But it gets more interesting here where you have hypothetical judgments. So an assumption that variable X has some type actually means, oh, the thing you're going to substitute it with has that type. And you can take advantage of that in a very nice way. And then finally, we'll talk about kind of scaling up. So that's, and these are just the first and second halves of the tutorial. Okay, so I handed out instructions already. Some of you are probably partway through with this, but there you go. All right. So we're a little bit behind, but maybe we can have a little brief discussion in the room. Do people want to briefly introduce themselves and talk about any experience they might have had using this or any initial questions they might have? I'll start. I'm Jonathan Aldrich. I'm from Carnegie Mellon University. I've taught with SASyLF in 2 kind of serious programming language courses the last couple of years, and a little bit with other courses like program analysis before it. And I'm interested in how to make, well, I guess my professional interest here is how do we make SASyLF even better, easier to pick up, more flexible, give students better feedback. So that's one of my kind of goals related to this area. Talia?
I can go.
Yeah, go ahead.
Sure. I'm Talia. I am a professor at BYUC. So I do work on proof automation, and I have a grad class on proof automation recently for proof assistants. And one of the big challenges has been getting people to understand what a proof really is before you build the automation system. And so having a nice term language would be really cool. And in practice, we end up jumping between ACTA and POP just to force people not to use tactics and then have to use tactics later. So yeah, this is one of the things that's been on my mind.
Someone else like to share their background, their interests, their experience?
I'm Hirsch. I'm a professor at University of Buffalo. And last semester I taught a PL theory course and we used Idris. And it was a lot of fun. But I think a lot of the students just found it very overwhelming because they're having to learn all the Idris concepts and all of the PL concepts at the same time. It was just a bit too much for them.
Excellent.
I'm Ankit. I'm a 5th year PhD student at Northeastern University, and in our my advisor in his logic and computation class uses SASyLF theorem prover, and we have been developing a proof checker for proofs written in Dijkstra's style of paper-intensive proofs, which require you to write your context, derived context, and then LHS with some justifications transforming into an RHS. So yeah, I'm looking forward to it.
Excellent.
Hi, I'm Scott. I'm a PhD student at Stanford. I do some work on theory proving and lean, and I'm generally interested in teaching PL and compiler concepts and introducing people to theory provers.
Excellent.
I'm Nishant. I'm a 3rd year PhD student.
Sharing is working.
I have an interest in teaching from my undergrad. That's a career I want to pursue after grad school. I also, for scheduling reasons, only recently took sort of a formal PL class, but I've done some work with assistants, obviously through my PhD. I'm interested in sort of the idea ideas in this tutorial, kind of put everything together, especially as a grad module. This is pretty, in my experience, it's been pretty, proof assistance and PL semantics, all this stuff can be pretty gnarly as a beginner. So it's interesting to see how to like simplify this stuff, or how to sort of onboard students from this.
Yeah, great.
Professor Olson, Delta University of Technology. So I'm assistant professor there. I have extensive experience with working with Magda, some experience with working with Cobb. I'm teaching courses that are sort of adjacent to BL theory, or that they are. I could be using more of the theory concepts to teach them, but I haven't really had the courage to expose the students to proof assistance there yet. SASyLF.
Okay. I hope so.
I'm Nathan. I'm a PhD student at UT Austin. Before starting my PhD, I was a sessional instructor back in Canada where I taught undergrad PL. And last semester I took grad PL in a software foundation sort of curriculum. So that sort of got me excited to be thinking about, like, in particular, how can we apply things like theorem provers to freshmen, like early undergrad CS classes, to get them sort of on the right foot and thinking about these things.
Any others want to share?
Sure. I'm Aldrich. I'm currently a PhD student at Brown, working in CS education. My primary is actually the education side, not the PL side.
Yeah.
But my first exposure my primary exposure to proof assistance, I took at a Chapala's class in undergrad, and that kept me up many a night. So I'm interested to see how easy this could be.
Yeah, great. Okay, well, I don't need to put everyone on the spot, but hopefully I appreciate hearing what your interests are and some of your experiences. So hopefully we can answer some of the questions that people have. So I'll turn it over to John for this next part. And we have, I have Eclipse right here.
Fantastic. Can you put up yeah, I'll find a new one. So,
Okay. Yeah.
So just go back to, is in Chrome.
Oh, just Shift Tab. Alt Tab, sorry.
Yeah. There we are.
Oops.
Alt Tab, I always find.
There you go.
Okay,
Yeah.
so trying to introducing students to proving, I find that students will know context-free grammars. I mean, we have a prerequisite course that teaches that, and they may have seen inference rules, but I find that students don't really understand what inference rules are, at least my students. And the idea that you need to know substitutions and unification. And often the prerequisite course will mention unification, but actually having people have a real intuition of that can be difficult. I provide I made a little interactive tutorial webpage that is available in the repo if you get it. It's just an HTML page, and it has you type in some exercises. It has about 10 exercises, substitution, 10 for unification. One of the big issues I find is adequacy. This even is an issue when I'm like reviewing papers from people for journals or conferences. People will have a bunch of formalism and just assume that that does something. And so people need to be disabused of the fact that just because you have a formalism, it actually does what you think it's going to do. So you can start with, say, a flawed axiomatization and start working with the students, and they realize, hey, wait a minute, this isn't working. Okay, so now we have to decide, what does it mean to be having this thing work or not? And so often an interactive sort of system will try to demonstrate that at some level is important for demonstrating the importance of adequacy. SASyLF does case analysis at one level, just a single level of case analysis, and that corresponds to the way usually people do proofs. And so for our first homework at UW-Milwaukee, the students take some axioms for plus and say, well, what rules could be used to say prove 2 + 2 = 3? And that gets them thinking like, wait a minute, 2 + 2 isn't 3. But okay, what rules, if we were to try to prove that, how would we prove it? And it gets people thinking about the rules formally rather than only thinking in terms of what is actually true. And then applying something to variables like x + x = x. What do you get from that? And so now I want to, let's see if I can go to the next slide here. This is sort of showing what I'm going to be doing. We're going to look at some easy definitions, look at proving some simple facts, prove impossibility of things like 1 + 1 = 1. getting into induction is sort of interesting because in a proof course, induction ends up being this very mysterious thing that students think is bizarre. But with SASyLF, I'm having people use a programming point of view. By this point in time in their career, students know how to program, and they know about recursion. So by using induction, the Hindley-Miller correspondence, not Hindley-Miller, sorry, that the induction corresponds to recursion, using the intuition of recursion to work on induction actually is very helpful. You need to have something smaller. So let's see how this works. Now, if I can do, let's see if Control Tab will actually get me there. No, it's not going to get me there. So I'm going to see if I can get onto Eclipse here. Okay, so now going to here, let's go. I'm going to in the, let's see if we can do a right click here. Okay, new SASyLF proof file. I'm going to call it live 1. And we'll just start here. Sorry, my eyesight's terrible, so, okay. Let's see. And the container is, I'm not sure why it needs to be specified. Yeah, it's not, this is not likely for me. So, I wish I was on my own one there. Okay, let's go in here. There we are. Okay, here we are on live. Starts off with terminals and some syntax. Terminals are things that we're just going to be talking about. I'll just put S in there. The syntax, I said, students will understand complex grammar. So if you put down these words like, say, natural numbers, we have n is 0 or its successor of another natural number, and they're going to be okay with that. SASyLF, it's common to put them on separate lines like that. And then we can save this, and we'll check the syntax of things here. And what do we have for our error here? Error says parse error, and that's wonderful because I need to give 2 colons here, which is, this is a case where we should have a better error message. So that's the syntax of natural numbers, and then we can make a judgment, say, for addition. And you give a name, and then you give the syntax. So we're going to have a natural number plus a natural number equals a natural number. And this looks all very nice to the students, and I tell them the equal sign doesn't mean anything. This is just simply a relationship between 3 numbers. And so we can make a rule. So for example, if n1 plus n2 equals n3, then we can have a rule, say, plus s, that will say successor of n1 plus n2 is successor of n3. And then we can try to prove various things about it. So those of you will notice I've left something off, but we'll get there. Let's actually make this a lemma. So this is going to be super simple. We're going to say that 1 plus 1 equals 2. We should be able to prove this if our system is adequate. So right away we notice that, well, we don't actually have a way to prove this, because if we want to use plus s, we would need to have, let's see, we're going to say, give a statement that, let's say result is that 1 plus 1 equals 2 by rule, say, plus s on something, and lemma. And we check this, and we see a number of problems. One of them, it doesn't understand this 1 plus 1 equals 2, because we never defined what 1 is. So we're going to define 1 as syntactic sugar as successor of 0. And we'll define 2 as syntactic sugar as successor of 1. So at least we now have something here. Okay, now we get an error down here. 1 plus 1 equals 2. And what is the error here? The what?
You define 2 as
Syntax.
like that.
I said @ sign, yes, no wonder, so it doesn't know, the @ sign would be fine. I said my eyesight is pretty terrible, so I really appreciate you helping me here. Now we have this one here that says we're proving 1 + 1 = 2. That's not the thing we're supposed to be proving. We're supposed to be proving 1 + 1 = 2. So now the one here says that we're supposed to prove this, but it doesn't say what these underscore things should be. And we can work backwards by going ahead on let's see if the quick fix works the same on Windows as it does on, no it doesn't. So how do I get quick fix? So how do I get quick fix, Jonathan, on a Windows? There it is, sorry.
There you go.
Okay, got it. So it's suggesting here's what we can do. We can use that to prove it. And as long as we have something that proves 0 + 1 = 1, if we have that, then of course we can prove this. So we can say that this would be on, let's give this first statement. Sorry, hello. Sorry, I'm just trying to navigate a computer I'm not quite familiar with. So, and we can't prove this because we don't have a rule for that. So this is showing just because you have some rules that say things, and maybe the things are true, it doesn't mean you're adequate. So we obviously need a rule that says 0 + n = n, and we need to give it a name. In SASyLF, we just put the rules over these minus signs, and just at least 3 minus signs, and realizes this is a rule. So sort of cute. So we have +0, and now it turns out then we can prove this by rule +0. And now everything's happy, and it's perfectly okay with this lemma here. Let's look at another sort of simple one that says if you have 1 + 1 = 1, then you have a contradiction. So how would we do that? How would we know if we have 1 + 1 = 1? How do we know we have a contradiction?
Quick check. Can people in the back see the text already?
Or does it need to be bigger?
You make it one size bigger.
Okay, let's try. What is the one? Is it Shift Control Plus or something?
That might work. If not, perfect.
Okay, good. It's a little bigger. Is that enough? Does that help a little bit? Okay, good.
And then question.
Yeah.
Those inference rules, do they have to actually go under the plus judgment?
They have to go under the plus judgment, but the judgments are allowed to be mutually recursive. So you can have a number of judgments that refer to each other recursively. That's okay, but all the plus judgments need to go together.
Okay.
Which usually makes sense in a paper. Usually put the judgments together.
Sure.
Yeah.
And so just syntactically,
Yeah.
there is a meaning to this.
Yes.
It's indentation sensitive or something?
It's not indentation sensitive. I just put them in there because I like that. Yes.
Is there a termination checker? How does that work?
Termination checker for the lemmas. If you do recursion, it's going to check to make sure that you that the thing is smaller. Yes.
So your rules could.
Oh, rules can definitely. I mean, at the beginning, I had a rule depend on another rule, and it was fine. It does check for syntax. If you have useless syntax, like a syntax that couldn't have any uses, it turns out that that would be unsound in SASyLF, so it gives that an error for that. Yeah.
Why don't we have a variable bounded by exists?
We don't use the exist symbol, but it is actually implicitly they are the things on these are for all qualified, and if it exists inside of a proof, if you could have we'll have one which will have maybe I can answer that question. Let's look at another a more interesting lemma, which would be that totality that says for all n1 and for all n2, I have to spell it for all correctly. That's actually a nice thing about IDE. It tells you right away, hey, I've misspelled something here. N1 plus N2 equals N3, and N3 is implicitly existentially qualified, if that makes sense.
It should be N3.
Yeah, it should be N3, not 3. That's going to be really hard to prove. So let's, and it's proved by improved, and so we can go ahead and save this, and it will just give a little mark that that thing is not proved yet. Little marker, I'm not sure if you can see it, it's sort of there's squiggly yellow under these things that are unproved, a little marker in the side here. That is a little smaller than the text because we made the text bigger. Yeah.
Also on line 28, what is the p variable reference?
Exactly. What is the p variable? This is actually an important thing because students will think of this as the important thing, 1 + 1 = 1. But when you're doing a constructive proof, you need to have the value that this thing is true. So this is the supposed value that we have here. This is a proof object that is, this is the one when we constructed the result, we constructed it by applying these rules. And this is saying, well, assuming you have something that proves this, actually you can't. Is this issue there? Yes?
I talked about that as a derivation.
Yeah.
And it's a derivation that ends in that statement.
Yeah.
So then you can like decompose that. And,
Or a proof object or something like that. Right, exactly.
Yeah.
Yes?
So in the latter two lemmas, there is a proof by unproved. In the first one, there is no proof by unproved, but the proof by unproved kind of denotes the end of the theorem statement.
Proof by is just a shorthand. I could have said proof by rule plus S here.
Okay, but so how do you syntactically denote that this is the end of the theorem statement and the beginning of the proof?
It has the end lemma. So, yeah. So you after you say exists, then it's the proof until you have the end. It's really very, very simple. It's nothing terribly fancy. Proof by is just usually the last thing is going to be proof by, whatever. And just to I could make this thing here be a proof by. Proof by was the thing I added right away when I was using too many buys. No. There we are. When I was using this, I found it was very repetitive to keep on repeating the goal whenever you had nested things. Yes?
So does it force this style of like having to define like ED1, for example, on the line above, where you use it inside of plus S?
You need to do one by one then.
Okay, yeah, so you can't like inline like plus D in.
You can't put it in two ones. Exactly right. That's actually it's a very important design decision. So now I'm going to have to find out what my error on line 24 is because I don't understand. Yes. So it's, yes, a normal form or let normal form there. So what is it unhappy about here? It just says
just save it. Just save it.
Okay. I was trying to do Alt S and that doesn't work, of course. So.
Right.
Yes.
PC.
Okay, so proving this is how we're going to prove that is true. What would be the idea of proving that 1 + 1 couldn't be 1? How are you going to have to do that? You have a supposed proof, a derivation that 1 + 1 = 1. How can you? And I'll just say there's no rule to prove contradiction.
Or we could prove it using ad absurdum.
Yeah. On what? So basically there's very few things you can do in SASyLF other than applying rules and applying lemmas, and you can do case analysis. So in this case here, we can say proof on case analysis on P, and what cases do we have? And I save this, and I've done another typo. What does it not like about it? 2 ons in a row. It is. I'm sorry, this is the fun of using the system. I'm not quite there. Okay, so it says there's an error because there's a missing case. It is possible using our rules to prove 1 + = 1. Well, at one level. So I'm going to show you a thing that we don't actually show students right away, so that you can actually click on this thing here, and if I can get it to click. And it will fill in the missing cases. So it is possible to use plus S, assuming we had a proof of 0 + 1 = 0. So I can write this as 1, it's the same thing. If I had this, then I can prove 1 + 1 = 1. It is possible. So students need to think, well, of course 1 + 1 is not 1, but how do we know that from the theorem? It's because the only way we can get it is by using plus S. And plus S as the input would have had to have 0 + 1 = 0. And it turns out there's actually no ways of proving that one. You can write case analysis on, and let's see if I can not do two case analysis here. And then I save it, and now it empty case analysis works. So we proved that. Let's look at proving totality. How are we going to prove that? Hint, we have to use induction. So, and that's not what I wanted to do. Sorry. Okay. So we're going to use induction on N. Induction on in SASyLF is actually short for two things. One is that we're going to do induction and that we're going to do case analysis. And induction means that we can call ourselves recursively as long as we have a smaller N, structurally smaller. What sort of time situation are we at right now? 2:45. What do you think, Jonathan? What are we going to do for that? I don't want to cut too much into your next level here. So that's one of the cases we're going to do. And it's going to note we have other cases that are necessary. And there's actually I have a, what? N2. Yes, I need N1 does not, N does not exist. I need N1 here. And it's a little bit happier. And we have an unproved case. And actually we need to have another case, and I can let it fill it in for us. Okay. And so it chooses a variable N0, but we probably want to call it N1 prime, because it's a bit different thing. So what do we do if we have 0 here? Which case do we use? If N1 is 0, how do we prove that there is some N3, which is existentially qualified implicitly, that 0 in this case plus N2 is N3? If you hover over the unproved here, that I am going to now hover over it, I'm not sure if you can see, but it says derivation of group 0 plus N2 equals N3. So it's done, it is shown what is unproved and what you need to do. So we need to have something, and what rule will do that? Well, rule plus Z does that for us. Now, if I just say plus Z here, and SASyLF will give a little error message that you forgot to say the word rule by. And it's like, oh, you need to have rule by, and you can fill it in with that. So, okay, and hereby on this one here, what are we going to do? Well, first we need to probably do the induction hypothesis. So we want to prove it for N1 prime. So let's get a P1, P prime, say that N1 prime plus N2 equals N3 prime by, and you can either say theorem total on N1 prime N2, or you can say by induction hypothesis. So by saying this, it makes it clear that this is recursion, and N1 prime is smaller than N1 because it's put in here. So we can go ahead, every time we save, it will make sure that everything's okay, everything's okay. So what do we do now that we have this? If we have a proof, let's look at what we need to prove. We hover over this guy, and it tells us we need to have something S of N1 prime plus N2 equals N3 prime. There's N3. And the rule plus S that we have will help us with that. So with that, I would like people to look at the exercise that we have in the system. And I think I have, let's see, by rule, I have too many N's. I'm sorry, I'm typing very badly here.
Let's see, you need N to be on.
Yes. No, I just had to say rule.
On.
Yes, on the P prime here. If I just said rule by plus S, we do get a reasonable error message. Let's see what we get here. I think we get a real message. It says wrong number of premises for rule plus S, which expects 1. So Jonathan, when they first did this thing, they tried to have good error messages, and I tried not to interfere too much with that because they are actually decent, and that's important for us. So that's with proof totality here. So let's see. Do you happen to have the other? I'm going to see to what extent can I go here without giving everything away here. Oh no, this is you have it. You have it exactly right. So this is the exercise. So if you have the exercise, you can start working on this now. And let's all look at it as a group. We can try looking at these various things. So this is the basic thing I had before. I defined a few more than we had before. I defined equality because equality is not built into SASyLF. If you want equality, you need to define it there. Let me get my mouse off there. There's plus with our 2. And I said, well, exercise, go ahead. Let's try to prove 3 + 1 = 4. I would like to have this thing have not quite so, can I add a space? Yeah, that's it. Another impossibility is to see how you can prove there exists a contradiction. Well, if you have something's here, you can prove anything. So then it sort of shows this is the problem with the proof system. If you're going to have proofs, you need to make sure that your formal system will never allow you to prove things are nonsense. And then down here is getting contradictions from a bad fact, just like we were doing before. Here's the proof of totality I did ahead of time. Demonstrating n3 is 3 at this point, in 2 cases. In ahead of time, I also proved something called plus unique. Sorry, somehow I am touching things. This is something also I'm going to want to show because this is not a relation. It's not a function. N1 plus N2 equals N3 is just some symbols. And so it could quite well be that 1 + 1 = 2 and 1 + 1 = 3. There's nothing stopping that from the SASyLF side. So you might want to prove this. Again, this is the equality relation that we just defined there. So in order to do that, to express that, you have to define an equality relation. Yes?
What is inversion doing there in contrast with the case?
What is the version?
Yeah.
Use inversion.
Oh, use inversion. So this is saying that this is the only rule that could apply. And so the inversion normally gives you the premises of a rule.
Is it basically an extension? Like, could you write that same thing by case analysis?
Yes, exactly. It's a case analysis of one case. And inversion is something you can always do something by inversion of. But in this case, the rule has no premises. So what does inversion do? If you invert +0 on P prime, what is P prime at this point? P prime is, what is N1? This where clauses are not required in SASyLF, but they're very useful for making it clear what is actually going on. From a pedagogical point of view, we added this to SASyLF to normally complain if you don't do that. It doesn't give a warning, it doesn't give an error, but it wants you to be very clear that you mean that N1 is actually 0 here. But by virtue of doing this case analysis, we know that N1 is 0 and N2 is the same thing as N3. So at this point, P prime is 0 plus N3 equals N3. N3 prime. And the only way you can get that is with the +0 rule. If you do this inversion, what happens is it forces N3 and N3 prime to be the same. That's the only way you could get that to be true. And so use inversion is saying, just for the side effect, I want to get this. So now it knows N prime is the same as N. It knows internally they're the same. And so we can use the natty rule to get the result we need. And here we have the one here where we're going to show that we need the plus sec for the first rule here. And we need to get, in order to do induction, we're going to need to get an addition on the other side. Again, we use inversion. If you only have one rule, you don't actually need to name it. It's perhaps a little sloppy, but you don't need to say, here I gave the rule. You don't have to name the rule. Again, it forces a pattern matching, and now we can do induction hypothesis to get these two things are the same. And it should be pretty clear that if those are the same, then the results are the same, but in SASyLF, it's just a relation. So we invert it to make them the same, then we use natty. So very explicit, every single step needs to be given. And I had some other things you could prove. The admissibility of a rule. Admissibility is a very important concept with rule systems. say, well, we could add a rule like this, but it doesn't actually do anything. So admissible really means redundant. There's no need to add this rule, and so we can show that this thing here, you can prove it just using the existing rules. So that's a useful thing to prove. And when people continue working on this, how would people think we need to prove +0 right? What would be, if you're doing it yourself or thinking about it out loud here, how would we prove that?
By induction on M.
Yeah, by induction on n. And so if n is 0, we need to prove 0 plus 0 equals 0, which our existing +0 will do. And if n is, say, the successor of some other number,
then we refer to the smaller induction.
use the inductive hypothesis, call yourself recursively, either one works, and then you apply the plus S or plus sub rule. You get there? Yes?
Question, you said that we start by proving by induction. Didn't you first have to do the case analysis?
The induction, in SASyLF, if you say proof by induction on, it forces the case analysis. You can also say, that the original SASyLF, that was the only way to do induction. And fairly quickly, we need to realize that sometimes you need to do induction on one variable, case analysis on a different variable. And so you can write use induction, which will tell you what we're doing induction on, and that's going to check termination of that. And then you say proof by case analysis on, and then you have case analysis on anything.
Would it be possible to do a case analysis just to have a redundant step in there?
You can have case analysis, yes. But if you just said proof by case analysis and did it, when you try to make your induction proof, and say, hey, you can't do that. So you have to declare your induction.
Yeah, imagine if I start by case analysis.
Yeah, no, that would be fine.
Need induction in the next step in one of the cases.
Yeah, so let's say you do proof by case analysis on n.
That's right. We distinguish declaring that the proof is by induction from later on using the induction hypothesis. So one is proof by induction, and then you go into the cases, and then somewhere inside one of the cases you say proof by induction hypothesis rather than just by induction. And that says, oh, we're actually using this theorem recursively.
So I'm just going to add a little case here.
Because now I would imagine that I would need induction in the first
Yes.
case. So it doesn't help me, but it's more specified.
Yeah, you'll notice that, let's say we have a p prime, where we want to say n prime plus 0 equals n prime by, and let's say we write it out as plus, I spell things right. And it says we're implicit, okay, so we have said we're doing, we didn't write out that we're doing it, and so we need to, let's say, induction hypothesis.
It's possible for him, but he advises you to use
Yeah. But at this point here, actually, because of a weird thing about the way we did mutual induction, we currently allow you to always do induction on the first argument, even if you don't say you are. So that looks unsound. So the induction hypothesis says, hey, you need an explicit proof by induction. And so what we can do at the beginning here, before our proof, if I can get it in here, use induction on n. So this is basically a declaration that we are doing induction on n. Yeah?
When you're doing induction, is there a way to see the kind of invert the derivation of the inductive hypothesis before you actually, like, it seems like it does infer something.
It basically, so when I say this, it's basically you have, it does not, let's see.
It's saying that you have to instantiate it to n prime, so it has some kind of inductive hypothesis that has like a for all n prime.
It's basically, yeah, you know how to do proofs. And so it's not, this is designed for people thinking recursion, not proofs.
Okay.
So the induction hypothesis is basically, as I said, just recursion. And so by recursion, you put an n prime there. This is a parameter. This is the output. This is what you get.
Okay, so but you have to know that you're.
Yeah. So it's for people who actually know what induction is, it's annoying. But it is, we're just thinking in terms of recursion, yeah.
Sorry if I get back to my
No, that's fine.
But when you wrote the case analysis and proved it by using the lemma +0, right?
Yeah.
Then you got the warning that you have done implicit induction.
Yes.
Is there a reason why you want to enforce doing induction instead of doing this recursion?
No, it's actually, it's that, this is okay here. It's because we didn't say use induction on it.
Okay. But you said that induction is basically like recursion for
Yes.
all the students, so I would say that if you leave the use induction on in and out, then it's like using recursion for the students.
Yeah. So I think you just demonstrated that we need a better error message for that, because it's not long that we use recursion, you left this out. Because it doesn't know, and it doesn't know that you are doing, recursion can only be done if you're going to demonstrate it smaller, and you need to declare that ahead of time. Because we have different measures. This is the one we're doing here, but you can do induction on any argument. In fact, you can do it on a series of arguments in lexicographic induction.
So you need to explicitly say on which argument you do
Yes.
induction or the recursion. So
Yeah.
you cannot infer on which argument.
It doesn't infer.
Yeah.
Yeah.
That's, I think, part of the general philosophy of SASyLF is that we try to.
It doesn't infer.
I think it's really reasonable to be explicit.
Yeah.
How would you otherwise know?
Now, why don't you go on to the next section, I think, because we're already at 3 o'clock.
Okay.
So you can start talking about the variable encoding type things.
Okay, sure, yeah. But no, if there are any questions come up along the way, please continue to ask. I'll make one addition to what John just said, which is that this idea of use induction on N, if you want to make an analogy to functional programming, it's like let versus let rec. Right? So if you make a recursive call to a function and you didn't declare it with let rec in OCaml, I guess, then I guess it won't be in scope. So this is like kind of like that kind of an error. But of course, it's slightly different because what you're doing induction on is important. And I think that's, pedagogy, just to, in addition to the general design philosophy being explicit, it's important because it demonstrates that the student knows what they're doing induction on, right? And we want to actually check that. So we don't want to infer it for that reason. Yeah, that's all. Yeah.
So it seems like there's a deliberate decision. Again, you said not to infer, but it's really not even like, it's like not inferring at the language level, but then there's this, or I guess if you're framework logical level, but there's inference going on in the quick fix kind of thing, where it's actually using. So I am just curious if that was a deliberate decision and how the people who use the quick fix a lot, like students, and how that, if there's information on how that's implemented.
Yeah, that's a great question. So we kind of do language levels implicitly. Language levels is an idea for teaching intro programming languages for those who haven't seen it. I think the Racket language has language levels where, you start out without lambdas and macros, and then because, if a poor programmer writes the wrong thing by accident, they'll get a completely inscrutable error message. But then later, you introduce those things as they are able to understand them. So we probably should have like a configuration flag or something about these, but we do it informally in classes just by sort of not telling people about.
Not telling people about quick fixes. We make them write it out by hand.
Yeah, actually, the first version of SASyLF has I think it's proof by search or something.
Yes.
Yeah, I don't know if is that still.
It's still there, but it works terribly, and it doesn't write anything in there. It's deprecated and unmaintained.
Okay, so we don't tell students about that one either for a good reason. But like simple proofs, you can actually search for a derivation, right? It's not actually that hard. And there's a paper on how to do it in 12th, which we can just use in SASyLF. So, but yeah, for pedagogical reasons, we don't tell students about that one either, and we don't accept it in homework.
Oh yeah,
that is really nice.
Yeah. Yeah, I think, if we were to, there's a lot you can do with SASyLF to make the production of these proofs, faster and more efficient if someone wanted to use it kind of professionally rather than pedagogically. Proof search and automatically generating things. In the end, you get a really long proof, but in some ways that might be good because it's sort of readable. You don't have to figure out someone's script. You just see what the steps are. Yeah, question.
When you say you wouldn't accept that on homework, how would you track that? Are you having people manually scan through these files, or like look through these files and look for like things that
It will make a warning. If you use solve, it will give a warning.
Oh, okay.
And so you look for warnings. And that's the same for unapproved. So if they didn't actually do the proof, they just said unapproved, it will show up as a warning.
I've never had a student discover that one independently, but I guess I'm on recording on it now. So if they watch this, tutorial, then they'll know the dark secrets. Okay, yeah. Other questions?
So I see this by blank on. Is that thing a tactic? Can you define your tactics? How many tactics are there?
I mean, it's like it's like a single step tactic. One thing you could look at SASyLF is, limits tactics to one step, and there's only a built-in set of them, right? So really, the only things you can do are induction, case analysis, applying a rule,
Prime lemmas and theorems. Yeah.
applying rules, lemmas, and theorems. That's basically it. So by inversion, that's just a form of case analysis. By contradiction, that's a case analysis with no cases. Really, it's just those things. If you understand that, you understand everything. Yeah.
What's your philosophy for IDE support? Like on one hand, you have stuff like Coq, which is very helpful in the sense of like showing you partial derivation trees, but it's also easy to sort of play it like a video game, to sort of use that stuff to try and stumble into an answer. Whereas this feels a lot more minimalist. Was that intentional? Is that just sort of an artifact of the design process of the language?
Yeah, it's intentional. I mean, I think so I talked about the benefits of proof assistance, but I think one of the dangers is the video game thing, right? I call it proof by Brownian motion, right? You just wiggle around a little bit, and if the proof is simple enough, wiggling it around eventually gets you a proof, right? So we'd like people to think about their proofs. I think, strategically, what I would say we do when we teach this, we use two approaches. One is, the first version of the language we teach, we don't tell about any of the quick fixes. We basically don't talk about much of the IDE support at all. And so students kind of get the mechanics at the very beginning, they really have to think of all the things themselves. Later on, we tell them about those things, but we're also giving them theorems that you actually have to think about. And so I think there's a balance pedagogically between how much support you provide and how much you get the student to do, and it probably increases over time. And probably, if we went further, at some point you'd want, more things like scripts and solve and so on. But I think, at the level we're teaching, that we've seen it as a pretty good balance. But yeah, maybe in the future we'd like to add more language levels and make them more explicit to support this sort of thing. It's a good question. So feel free to continue working on this, but let me move on and talk a little bit about programming languages and variables. So let's see here.
Slides.
Yeah, where are the slides? There they are. Okay, good. Right. Okay, so what's special about programming languages? What we've seen so far is just sort of proofs and proof assistance, and SASyLF is a particular explicit. It could be used in a math class, really, a discrete math class. We haven't really played with that. I think there are some other tools that are maybe close to SASyLF in the pure math domain. But what's really special about programming language is variable binding. And it turns out that it's one of the most important concepts for students. It's also the thing that's maybe the most hard to model in proof assistance. And so you can read the literature on all the different ways you can encode variables. right? And I admit to not being an expert on this because I'm spoiled by SASyLF and 12 and so on. But there's a lot of choices, and they all have trade-offs, and they're all a little bit complicated, right? I think you can teach them, but there's a cost. So we try to reduce that cost. So SASyLF provides two features that help. One is that we talk explicitly about where variables are bound. And this is something that we don't do. We often kind of slide over this a little bit on the blackboard. We don't necessarily write it down, but we generally say it, right? If I say, if I give you a, now I feel like I need a chalkboard too, right? If you say, let x equals E1 in E2, you really want to say, oh, x is bound in E2. But if you say let rec x equals E1 in E2, then x is bound in both E1 and E2, right? And this is actually very important. It's like the difference between those two constructs. So SASyLF makes it explicit. E of x means x is a variable that is bound in E. And then we have substitution. So you can say E of E2 means substitute E2 for the variable bound in E, which is x in this case. So again, it's a little more common in programming language literature to say E with maybe E2 prime for x. But because we have this notation for showing the variable binding, then as long as there's one of those somewhere in the rule, which there always will be if you're doing substitution, you got to have like a binding occurrence, then it's clear what you're substituting for here. And it's like if you have several things down, E of x, y, then it's the order. You state them in order. And this is a convention you do see in, it's a little less common in programming languages, but it's very common in math. And it seemed like the simplest thing we could do to show binding and substitution. So let's see, how we can model the dynamic semantics of the lambda calculus using this. Okay, so let's go here.
Live too,
Yeah, actually, I have this other. Can I open both of these at the same time? I think I can.
Yeah.
Hello. As long as Eclipse can figure it out.
There it is.
Yeah, there it is. Okay. So, all right. So let's do this. So I'm going to pull in all the things that John defined about natural numbers because I'm going to define the lambda calculus with numbers. So let's say, and we can pull in modules. So we say module natural equals org.SASyLF.util.natural. So we're importing natural numbers. And this is a library that comes with SASyLF. John produced it. It has a whole bunch of theorems about the natural numbers, including the one that we were just looking at, I think. But it isn't all the numbers all the theorems you could possibly imagine. So we give some that aren't in that library to our students when they're starting out. So let's define some new terminals. So we want to define successor and zero again, but we'll also define function for lambdas and value, which we're going to use in judgments. So now let's declare some syntax. We'll import n. So n is just going to be the n from the natural library. And I also want to be able to use the constructors from it, so I'll repeat these here. So you can repeat basically the interface of the library if you want to use the pieces of the interface without referencing the library in fully qualified form. And then we can get to the lambda calculus itself. So let's say expressions are variables x. Thank you. Or we can have function x. And so here you see, this is just like the lambda calculus with kind of I don't know, maybe a JavaScript-like notation, but some weird combination of JavaScript and ML, but we define this is like the binding occurrence of X, and that shows where it's bound. And then we've got application, and we can include numbers. Okay, so a couple of things about this, what's going on here. We use meta variables to denote the types of things, right? So any meta variable like E1, E2 is going to be an expression E. That's, again, just like comes from mathematical dimension. We need to know what kind of thing X is, but since X is a kind of E, and since X appears as a bound variable, then we know that this is a variable, and we know the type of the variable is E, right? So that's how we basically we're inferring things like the types of variables from the structure of the syntax that you would have to declare explicitly if you were in like Agda or Coq or something. The only other thing that's a little weird is this pound n. It turns out sometimes you need to write n, and you need to know whether it's an expression, or you want SASyLF to know whether it's an expression or a natural number. And so by like putting an extra symbol in, it figures that out. SASyLF was able to figure that out. So it's, I guess, a tiny little bit of encoding, but it's one that's pretty easy to explain and gloss over. And of course, so I guess we can also say, like we can add addition or something, right? So we can say E plus E, which is, we'll basically use the numbers library for that. Since we have variable binding, it turns out we need contexts, and this is something where I think we need to maybe clean up the language a little bit. I'll explain this notation a little bit more in the second session when we talk about type systems. For now, it's just something you have to add, and I think this is an uninteresting context. It doesn't actually say anything about X. And so I think in a near future version of SASyLF, we'll let this be inferred by the tool so that people can do kind of proofs about semantics that include substitution but aren't actually using like typing judgments that need to use something in context. Anyway, it's ignorable for now, and it will be, I think, completely eliminated in a soon coming version of SASyLF. Okay, but let's talk about some interesting judgments. Okay, so we'll import the plus judgment from natural.plus, and syntax is n plus n equals n. Just getting that from a library again. And now we'll define lambda calculus. So I'm going to show big step semantics here. And it's useful to know what a value is for those. So I'll just start with the semantics, and then we'll see that we need value. So let's have an eval judgment. E arrow E. So we have E value. Let's see. Let's do an interesting one first. So let's say we want to do add, right? E1 plus E2 goes to something. Well, this is a big step judgment. So we want to evaluate it by first evaluating E1, and we'll evaluate it down to a number, N1. And similarly, we're going to do evaluate E2 to a number N2. And now we have our library for plus, right, which is just the rules that John defined, but in a slightly nicer form in the library. So we'll just say, okay, if N1 plus N2 equals N3, then this evaluates to N3. I guess I'll put the marker on it. Yeah, I should name the rule. And it tells me if I don't. Okay, so eval add. Okay. Now, if it's already a number, so we could say pound N1 goes to pound N1, and we could call it eval num. But I'd really like to do this for all values, right? Functions are values. At my school, the functional programming class, all the TAs wear a shirt that says functions are values because at one point they asked a question on a quiz, are functions values? And like half the people said no. So now all the TAs wear it, no one gets that question wrong anymore. So let's make this a little more generic. We'll say that E goes to E as long as E is a value. And then we'll need a judgment for values. Makes things a little more, we wouldn't have to do this, but it makes things a little more clean, right? So now we have N as a value. So that's like val nat. And we have my favorite slogan from our functional programming class, that functions are values. E of x is a value. Okay, I don't have any typos yet. Okay, so that's we've done most of the fun parts, but let's add a little bit more. E1. Okay, so let's say we have E1, E2. What does that evaluate to? Okay, so now here's the fun of the lambda calculus, right? So let's do our normal big step thing, right? So we'll evaluate E1 down to something, and it should produce a value. And we need this value to be a lambda expression, so we'll just write that in here. E of x. And E2 will evaluate to some other value E2 prime. And so now we want to substitute E2 prime into E and then evaluate down to a value, right? So we can write this pretty much just like we write it on the whiteboard, except using the particular substitution notation. E of E2 prime goes to E. And so that means substitute E2 prime for the first variable that's found in E. In other words, there's only one, so it's just x. Yeah, now we're basically done, right? My notes I have this as E prime, so I'll call it that, and this is eval call. Okay, so there's the lambda calculus. So it's nice. You see, I guess you have to know what the notation is for substitution and for variable binding, but you don't have to encode variables as integers or anything, which is kind of nice. Yes, question.
For eval add, can you go over again why you don't have a pound sign on line 41 or anything? E1 evaluates the number, E2 evaluates the number.
Right. So pound sign is not built in. Pound sign is the symbol that I use to embed numbers in expressions. So my language is not quite the normal lambda calculus. It's basically the normal lambda calculus, but whenever you write a literal number, you got to put a pound in front of it. But the judgment for plus just has n plus n equals n. And pound is not part of the syntax of numbers, so that's why. Yep. Yeah, question.
Does it still work? I tried it once and
Yeah, it's fine, except at some point you may have an ambiguity because you're saying that you don't know which is
Yeah, it'll work fine, but then at some point you'll be like doing a proof by induction, and I forget exactly how it manifests, but yeah. Basically, it has to. So we do this trick, which is very useful. 90% of the time, it corresponds to what mathematicians do, which is we infer the types of things from the names from their names, right? So if you have a variable type expression, it's got to be E. You can't pick F or T or anything else, right? But there's a lot of letters in the alphabet, and you can use Unicode and SASyLF. So really, you've got as many as you might want.
And you can put multiple. You could say E comma F on line 14. You could say E comma F.
Oh, okay, yeah, that's cool.
So you could have multiple.
Did you have that?
Yes.
Yes, excellent, okay. I was saying, I didn't remember that part. Yes, question?
So pedagogically, your judgments look a lot like what you would see both in text or on the blackboard.
Yeah.
What is the philosophy here? Like, if you were teaching mixed mathematics in a class, would you begin with something on the board, or would you be doing like essentially what you're doing here, where you're mapping it directly in the proof systems?
Yeah, so I think maybe we do it different ways. I do it on the board first, and then we show them how it translates to SASyLF. And in fact, on the board, I give them the semantics for substitution. Like, I show how it actually works. Here, like, I never had to define substitution. SASyLF just knows what it is. But you do the same thing, or you do a slightly different
Basically,
approach?
but I just sort of type in, I do on the board, and then I never say that I'm doing SASyLF for the book, because it's so close. The idea is to make it very close.
Yeah. Yeah, so and in fact, if you want to teach substitution in SASyLF, you can, there's a way to do it. You just, you don't use this syntax for variable binding. You just define, variables as numbers under the hood, and then you can write the usual rules for what substitution means.
We really want to do this to round numbers.
Yeah, you can actually do the variable encoding if you want to in SASyLF, but probably maybe you want to do that to teach substitution in the first place, but not otherwise. Yeah, because it's quite handy not to have to do it. And you can, of course, you can do things wrong, which is part of the problem, right? So SASyLF, because you have this variable binding, it makes it harder to make mistakes in adequacy, I think. You still make mistakes, and you can always make mistakes in adequacy, but there's a class of mistakes that kind of go away, which is nice. Okay, let me show, we have 5 minutes. Let me show a theorem, and then maybe we'll have some time for questions and playing at the beginning of the next session. So this is a theorem actually I proved this in class, and then we showed them in a recitation how to prove it in SASyLF. So eval should always produce a value, right? Okay, URM. Okay, so for all derivations, E1 to E2, there should be a judgment that E2 is a value. That's how we show that we always produce a value. Okay, so proof. So how should we prove this? I tell my class there's always only one answer. Induction, yeah. If you say proof by induction, if you yell out proof by induction in my class, you're always right, basically. Sometimes you can do proof by case analysis, as John showed, but not for the interesting ones.
Yeah, so you unbanded it, and I didn't.
Yeah, okay.
I added that feature too.
Okay, so let's see. I can save some time by saving, and we'll have SASyLF generate the cases for me. Oh, that didn't work.
Double click on it.
Thank you.
I can do that because I had the same problem and press on nothing happened.
Oh, I just double clicked. I was right clicking I think I got it to work by right clicking, but it didn't work that time. But this time I double clicked. Thank you for the hint, John.
Does double click not work for you? Okay.
Okay, yeah. All right, so yeah, you have to get rid of the syntax errors before it'll produce the cases for you. Okay, so induction on D. So we've got like all the rules for evaluating from one thing to another. So let's go through these. So let's say that E2 evaluates to itself because it's a value. So how do we prove the result?
So you can hover over there, and I'll show you what you need to do. Hover over on proof.
I need to show that E2 is a value. By assumption, okay? It's right there. So the way you say, of course, we want to be explicit about which assumption it is. So when SASyLF generates these, it just puts an underscore in, but we'll name it. We'll call this D1, and then it's just by D1. So that's done. Okay, this is like the simplest proof ever. So let's say we're doing a val add. Okay. Thank you. Yeah. So we have to show that this thing we're developing is a value. So how do we know that a number is a value? There's a rule, yeah, and I forget what it's called too. I think val num.
So what you can do is say val and then do escape space.
Escape space.
No, escape dot. Sorry.
Escape
no,
dot.
No, control dot. Control space.
Control space.
There you are.
Oh, look at that. I didn't know that. That's awesome. Valnat. No, nicely, it didn't tell me which one, right? That would be too much. Okay, so autocomplete works. Okay, so that's easy. Now the third one is only very slightly more complex. So the val call, we want to show that the result is a value. How could we tell that the result is a value logically here? By induction. Okay, so we said we were going to work by induction, and we haven't used the induction hypothesis yet, so this must be the time, right? Okay, by induction hypothesis, and we have to say what it's on, and it's on the thing that produced the E2, right? So our input was a derivation of this whole thing that ended with a call to a val call, and the subderivation is this tree, and we're working by induction, so the theorem must be true for all subtrees, including this one. And so we just give this a name. I'll give it the name D2, derivation 2, and now we're done. Okay, and so again, okay, so I guess this was swept under the rug, but when we generated this case rule, you see it actually instantiated the call rule by substituting in these pieces for the cases, right? So it substituted in fresh variables everywhere, and in particular, it shows this pattern of binding, right? We get an E5, that E5 gets substituted in here, and so we're kind of implicitly using the substitution in a nice way. Oh, and another thing that's kind of fun to show here is that SASyLF generated these parentheses. I don't know what's going to happen here, but I think if I erase these, it still works. SASyLF has an interesting approach to parsing. You may have noticed that you can just specify a grammar and then you get a parser for it. It's kind of nice, right? If you know anything about grammars, that's a little bit suspicious. So what we do is we use GLR parsing, which will parse any grammar, but it might be ambiguous. So it turns out if it's ambiguous, SASyLF just gives you an error. And what we've done is we've built in parentheses. So if you want to, so basically you just write parentheses around any constructs that you need to make parsing ambiguous. So SASyLF doesn't know that addition is left to right, associates to the left. So you got to put in parentheses if you have n1 plus n2 plus n3. Generally not a big deal, but what it does is it means, okay, if I haven't taught ambiguous grammars in my programming language class, I don't have to. And I guess maybe more importantly, you can work with things that are much more like abstract syntax trees and not worry about the concrete details that actually make things parsable in practice. Okay, so it's coffee time. Why not leave you here? When we come back, I'll give you some suggestions, but basically what I've done here is just the first part of exercise 2. So, if you want a head start, there's a couple things you can do, like add a let statement, fix up this proof that we just did, and then there's a proof that relates to big and small step semantics. So we'll come back and spend maybe a little time on that in the second half, and then we'll show type systems and how substitution and variable binding work with type systems, which is actually really interesting because the context that X has type tau actually means there's a judgment whatever you're substituting in has that same type tau. And so it's a very nice correspondence. This comes from 12. We didn't invent it, but we did make it look, I guess, we made it look pretty. So that's what's coming in the second half. Thanks, everyone.
Nice.
Thank you so much.
No problem.
Yeah.
I'm not that like, I just like, because I'm staying in the first place. And we also called another
Okay, why don't we get started? We may have a few more people filter in, which is just fine, but I'll make a couple of higher level points. We'll have, what do you think, John? Should we have, we're a little behind, but should we have 10 minutes or 10, 15 minutes of free time, and then you can dive into the next part? Okay. So what's interesting is notice that we define the dynamic semantics of the lambda calculus without giving rules for substitution. So that's because SASyLF builds in variable binding and substitution operations. When I teach it, I do give students substitution rules on the blackboard, which helps in understanding how it actually works. And I think, broadly, this has benefits for students using proof assistants. It means you don't have to necessarily cover variable encodings in the class unless you want to. They tend to be complex, and unless one of your goals is kind of a deep understanding of proof assistance as an explicit learning objective, this might not be in the scope of your PL class. But if the proof assistant is not a main objective, but more a means to the end of understanding programming languages, then I think that's where SASyLF has some benefits. And like I said, you can encode variables if you want to. Anyway, going back to our example here, let's see. Yeah, that's the live coding demo. Exercise 2.SLF. So this is in your directory. So there's several to-dos here, and I encourage, maybe some of you have started working on them, but I encourage you to look at them if you haven't. Yeah. Well, maybe I'll go through them. I'll go through some of them, like John did, as a group, and I'll take questions along the way, and then we'll spend maybe 10, 15 minutes. You can play along or work ahead of me if you want, and then we'll switch to the last piece, which is the type systems. Okay, so the first task is to add a let construct. So to do that, you've got to add a couple of terminals, and then you can add here. So how would you add a let construct that can express, say, let x equals 1 and x plus 2?
Is this supposed to be a recursive let?
Yeah.
We can explore. It's a regular one, but we could do the other one as like an alternative.
Then I think it would just be let x equals e in ex.
Yeah. Good. And if you wanted a recursive one?
I think the first one would also be the ex.
Right. Yeah. So that would be like letrec, which of course now it complains that I haven't declared the terminals. But yeah. So actually, that's the only thing that's kind of syntactic about the only thing where it was a hint of a parser is that you declare your terminals. The other things, thankfully, we're able to eliminate because we have the GLR parsing going on. So we don't have you don't have to declare precedence or anything like that. Okay, so actually nothing goes wrong in the rest of the code except that well, it's interesting. If you wanted something to go to wrong as soon as you added let, then you'd need like a program that used let and then discover that, oh, it doesn't, I can't prove that it evaluates to anything, right? So we could write a little theorem that says let reduces to something, and then that would test our semantics.
The theorem is still true. It only says things that evaluate go to values, but things that don't evaluate, that's okay.
That's right, yeah. Okay, but we can add a big step rule for let. So what should we write? Let's say it's eval let, and we have let x equals e in, and I have to give them numbers here now. So I'll say e2 of x. And this will be a big step. So yeah, someone want to suggest what I should write here?
You do E1 evaluates to E1 prime.
Okay.
And then E1 prime substituted to E2 evaluates stuff like E prime. Then the whole thing will evaluate to whatever it is.
Okay, super.
Now,
Looks right to me.
Down there, I think you'll have a red mark.
Yes, now we have an error. Okay, so our proof had a case for every evaluation rule, and now we're missing a case, right? So not surprising. So yeah?
If you were to not evaluate E1, but just substitute it, would that work?
Oh, interesting. Yes, it would. Well, first of all, it's accepted. Secondly, it's yeah. So that's interesting. We have no state in this system, so it should produce the same final result.
Just slower.
It's slower.
It could have some sort of omega problem.
If you get it, so if the result is a number, it should be the same number. If the result is a lambda, you might have substituted something different, something bigger into that lambda. So you might get a syntactically different thing, even though it's semantically the same. Yeah, so actually it'd be very interesting proof to like compare this to the other rule and see what you could prove. I guess you should be able to prove some kind of equivalence with an equivalence relation. It's hard. Yeah, it sounds hard. I don't know if it's any harder in SASyLF than anywhere else, but it's hard, just in general. Yeah, okay, so so I've added small step proofs, so you can see what small step proofs are like. It's nothing really surprising here. Except, yeah, so we got more rules, right? So for add, we have 3 rules. The one that adds the numbers, and then 2 context rules. We only evaluate the second one if the first one's a value. I chose left to right. I guess we could leave it non-deterministic. That would be fine semantics, although a different one. But now we could also add rules for let, right? So let x equals E1 in E2 of x. Small steps 2. So what would we write here? Suggestions?
Can you do the case where E1 reduces first?
Yeah, okay, so let's say E1 reduces to E1 prime. And then we get let x equals, it'll be E1 prime, right? And E2 of x. That would be a congruence let. And then
Context.
Context let. Or, yeah, context or congruence. So pick your favorite term. Okay, so what would the other rule look like? If E1 is a value, good.
E2, E1.
E2 with E1 substituted in. Yep. Reduce let. Okay, so SASyLF's happy about that. Now let's fix, this is the theorem I proved in the live demo. So proof by induction is missing a case.
For some reason it decided it doesn't like you. Double click.
Oh yeah, I guess I got to double click. I swear I gotten right click to work.
Yeah, Eclipse is weird.
Oh yeah, okay, so 3 of these cases we already proved, but I was in a different file. So, we can prove, I guess we can prove the lot one since we didn't prove that before. Yeah, so what is this proof by? It's a lot like one of the cases we did already. So we're trying to show that in a big step semantics, that big step always produces a value. So we want to show E2 is the value. How would we do it for this case?
You do assumption on the second.
Okay, by assumption on the second one, let's name the second one, second premise. Proof, so by assumption is just saying proof by D2. Oh, no, okay.
Error message will be useful.
Yes, error message will be useful, okay? Provided derivation doesn't match. Okay, so we provided the derivation E4, E3, arrow E2, but we want to show E2 value. Okay, so actually we do want to use that derivation, but what do we want to do with it? Oh, small step, okay. Well, I'm in big steps, so I don't think I want to use, small step.
Use induction.
Use induction, okay. So the answer to everything. Okay, so in this case, the induction hypothesis is going to work, and the reason is, of course, so this is one of those things, right? Students need to actually think about like why does this make sense, right? So how do we know that E2 is a value? Well, we don't know right away. If we knew right away, then it would be like a proof by rule or something. We know because this is a piece of the derivation tree, and we're working from small derivation trees to big derivation trees. So this is a smaller piece, therefore we can use the induction hypothesis, right? It's producing the thing we want to show as a value. So yeah, so it's by induction hypothesis on D2. Okay, good. So the rest of the proof is I showed before. I'll let you fill it in if you want. But then there's this last one. So actually, this is kind of a big one. But maybe. Oh, well, we're already 15 minutes in. Okay, I'll do like a step or two into it just to give you a flavor, and then oh yeah, I didn't write the cheat sheet for this one. Okay, so
do a quick fix and then look what happens with us.
There you go. Okay. So proof by unproved. Actually, to do a quick fix, I think we have to get the big principle first, right? So actually, here there's not much to do, right? We do either case analysis or induction, either on. We could do it on these pieces of syntax, but that's kind of maybe not so obvious. But there's one derivation, and it seems like we could do syntax on it. Oh, I should say, what is this, right? We define a big step semantics, we define small step semantics. What we're showing is if big step shows that E1 evaluates to E2, then through 0 more steps, E1 should reduce to E2 in the small step semantics, right? So it's 1/2 of the equivalence of these two. And then the other, there's like a corresponding theorem that goes the other way.
So maybe I just missed it. Did you define arrow star explicitly, or is star defined in the library?
I did define it explicitly, yeah. So yeah, nothing magic about star. There's a judgment E, arrow star E. And I've defined it as either the recursive case, E arrow star to itself, or it takes one step and then 0 more from there. Okay, yeah, so that's a great question. So that's the multi-step judgment. Again, kind of a common thing people provide. Okay, so since we only have one input, we might as well do induction on it, right? We could try case analysis. Well, we could try case analysis and then we could add induction later, right? Someone was pointing out maybe this is the best way, you were pointing out this was maybe the best way to do it pedagogically, right? So let's do case analysis. We could still do case analysis like on the expressions too, but this is kind of a heuristic, right? If you don't know exactly how the proof goes, you don't know what to do, but a heuristic is, starting with the derivation is often better than the syntax, just because you have more to work with. Okay, so we'll do end proof and case analysis. Thank you. Why pair programming is better than programming by yourself, right? Okay, so let's insert the missing cases, and then add, I suppose. Is add like the one that's interesting but not too hard? I think so.
We won't finish it.
Yeah, we won't finish it. Okay, so we're trying to show. So we have a big step for add, and we want to show that this turns into a small step, right? So how could we do this?
Well, by induction, we should be able to obtain a sequence of steps that reduce E naught to a number, and equal steps to reduce E3 to a number. At that point, I would want to maybe appeal to a runner that.
Okay, brilliant. I love that strategy. Well stated. Okay, so I'll restate as I type it, just to make sure everyone in the room can hear. So E0. Okay, so we want to show that if E0 steps to some number with big steps to some number, then there should be a sequence like an arrow star that says that it does that, right? Induction hypothesis on, we need to give these names. D1, we're going to need all of them eventually. D1. Okay, so that'll be our first step. And what did I do wrong?
You didn't name your derivation.
Oh, thank you.
Now,
induction hypothesis requires explicit proof by induction. Okay, so now we find out that we
go to the beginning. They don't change it. Say use induction line.
Perfect. Okay, so now our first step is make sense. Okay, so right. So we'll have a D5. So your next part of the strategy was to show that E3 goes to N1 by induction hypothesis on D2. Let's see. Okay, and so now, sorry, should have shut that down, I guess. Okay, so now we got to paste these together, right? We got to show. So that should be conceptually easy, but it has to be proved, right? So if E0 steps to N0 and E3 steps to N1, then E0 plus E3 transitively steps to N2 if that's the sum of those, right? So we'll have a lemma add I forget what I called this in my earlier version of the proof, but add composes or something. Add sequence. Or I could, actually, you could just have you could just paste, well, you could paste these two together, and then you could put that at the end. But the way that's actually going to require one more lemma to paste something at the end, because we would define arrow star by adding something to the beginning. Anyway, there's several ways you could do this. But I'm going to choose to use a lemma on D1, D2, and D3. And now we'll have to define it, right? So actually, is this a quick fix too? Oh, parse error by lemma.
No quick fix for that.
Okay, no fix for that. Okay, so we've got to have.
If you don't want to do D3.
Oh, right. Thank you. It'll be D4, D5, and D3. Okay, so I want to paste together this thing that I got, that thing that I got, and this thing that shows that they add up to N2 in particular.
And we may want to switch over now.
Yeah. Okay, so we could define a lemma. I think you can kind of guess how to do that. It's just like defining a theorem, except, well, actually theorem and lemma keywords are interchangeable. So it's just what you want to name it. And yeah, let's continue on, because the next piece is exciting. But I suggest if you want to like play with this proof, it's kind of fun to finish. And this is like, well, but it's actually hard to do the whole thing, right? I just thought we might get started with it today. But this is the main thing that students do for one of their homeworks in my class. One of the early ones. Okay.
We can switch actually to live 3 and go straight to the live 3.
Oh, okay. Super. Live 3. There you go. Take it away.
Okay, so I've been during the break. I typed in some syntax here, and we have the syntax of terms, and I decided we can have it called either T or U, just to sort of demonstrate that. And we have variables. I'm doing T instead of E, but of course, just to be more. Excuse me, I'll take off my mask. A little more TOPL-like there. Lambda to be more TOPL-like. We have unit instead of numbers. There's some types. And we have the context we had before here. What we're getting a complaint about, let's see what the, this is not GIMP, this is not star.
You need a recursive case.
Yes, you need a recursive case for render. SASyLF is very strict about the way you do your context. So I got all those errors because I did not define context like that. So context, because this is going to represent an LF context, in other words, assumptions that are in the context, it has to be a linear recursive thing. That you can put it on the right or left, it doesn't care about the parsing, but the idea is that there can be some chunk of stuff that it doesn't really analyze and also empty. And then we have value as before. We have unit as a value, and of course, functions are values. I have the small step semantics here. And it's complaining about value because we need that as a keyword, in other words, a terminal. So I'll just go ahead and add that to the top. And people are happier here. And we have our small step semantics with the standard TOPL names of EAP1, EAP2, and EAP tabs. Should be. Got our, there. So unit, of course, doesn't evaluate anything. So is this all, this should be all really familiar to anyone who's done the lambda calculus. Now, of course, we need a typing judgment, and that's where the fun thing happens. Okay. So we're going to have typing, and we're going to write that as T has some type T in context gamma. And I need to have a colon there. I don't have to have a colon, but I would really like a colon. Yes, thank you. Now, I'm going to do something special with here, and this is very specific to SASyLF. Assumes gamma, and what this means when I say assumes gamma, this means that gamma is not actually syntactically part of this relation. The gamma that's here represents things in the LF context. These are hypotheses that can influence how we're doing our relation. So the relation really is only 3 term syntax. And then this, since it assumes, is just in the background. You can't do pattern matching on it. But you can do the standard things. Let's look at the standard TAP rule. And the TAP rule, I like putting indenting, but that's not necessary. We have T1 and T2. So let's see if I can make this on the screen here for a bit. So what does T1 have to be? To be typed. How many people are got the, yeah. Arrow, yeah. I'm going to say T arrow, T prime. But yeah, there has to be some arrow type. And then, of course, then T2, we're not doing any subtyping nonsense here, so we just have T2 has to be T. Doesn't have to be an arrow type, but it needs to be the input type, and then our result will be T prime. Okay. So let's see how SASyLF is okay with this. Okay, so we have that. And then we have T-abs. This is slightly more interesting. So we have one of these things. That's going to be this is the function, so it should be an arrow type from T to some other type T prime. By the way, here I'm using an explicit type T, but it's perfectly possible to do the entire thing with, I forget whether this is called the Curry or the Church semantics, where you leave off the type and infer it. SASyLF doesn't care because it's just a relation. But here we're making it explicit. So what premise do we need here for, how do we know if this is well typed? Well, we're going to need to have that T of X needs to have what type? T prime. But of course, inside there, X might occur. And so we need to have an assumption about what type X has. And so we write that in the standard way, in the sort of a TAPL way. We write the assumptions on the left-hand side of the turnstile. And what this assumes gamma means is that this is actually going to be, it's going to be in the LF context. So actually, we're only going to be looking at T. So while we're typing this, we're going to have this extra fact here. Do I have to have, I'm sure I have something wrong here.
No prime. No prime.
That should not be prime, thank you. Yep. So we're going along here, and let's see, what is unhappy about this? I need to give the name of the rule, thank you. Let's call this T-abs. Okay. Now, but we haven't actually said what this means, because it sort of looks like that says X that have type T, but of course SASyLF doesn't know that. You just rewrote that as syntax. What does that actually mean? We do that by having a very special rule. We're allowed exactly one of these. A rule that says gamma, and you can put something on the left-hand side in the conclusion of the rule. And this rule looks very innocent, because there's a lot going on here. This is T var. And what this says is that how do we interpret this thing on the left-hand side? How are we going to interpret this context? He says the way you interpret it is that what's going in the context is that X is type T, this relation here. So the fact that this is the same and this is the same we decided to do that. We could have done a different syntax for the context. This is the syntax for the context, this is the syntax for the judgment. This is a system where we're actually using, if you use a variable, it's going to put the typing relation in the context. And that's the only way you know you have a variable, it will have a typing relation in the context. Which means it's not possible to ask, hey, am I a variable? Because all you know about something is in the context. In the exercises I give from UWM, I use a different way where I have a judgment, a hypothetical judgment that's true only for variables. And we have something called isVariable, and then you can it causes certain things to be more complicated. Here, I just want to say, this looks very innocent, and you can sort of think of this as saying, well, the last variable could have that type. And what about some other variable in the context? It's not the last one. Well, you can do weakening. You can always do weakening in SASyLF, add more things into the context. So you can get this thing here, then if you want to have more things in the context, you add them. So, okay, now we have typing, and of course the classic thing is we want to show that we have progress and preservation. So let's look at preservation. What does preservation say? Because we can just have type systems. I mean, this happened all the time in the 90s. People just had a paper at like eCoop or POPL or something, or maybe not a POPL, but at least at eCoop or OOPS or something like that. And it's not a type system. It's like, it's great, we have a wonderful type system. But after TAPL, people are like, oh, we actually need to prove that this type system actually has some property we want. So preservation. So what does preservation say? Yeah. Types are preserved through small step evaluation. So we're going to say if we have a typing, and I'm going to do gamma for now, but we're going to change that. And that we have an evaluation, then we have that. Someone else? T prime is that type. So this is the classic preservation thing. And where did I switched it?
Go back to live 3.
Yes.
You can click on the tab above too.
Okay, yeah, thank you. I'm very ham-fisted with my typing, so. Okay, so there's a warning here about, because gamma is a context. This theorem is actually true, but there's something interesting about it, because gamma is talking about things that are in the context. Now, T here is in this relation, which does not have a context. Since T is in a relation without any context, it means T cannot have any variables in it. Otherwise, this would not be well bound. And so there's no point in actually having a gamma here. It's technically true, and you can prove it, but there's no, the corresponding thing in progress is that if you say if this, then that, you can't prove that. Progress has to be proven in the context. And TAPL does that correctly. Here, TAPL does it with gamma, but it turns out that the context is not interesting because you can't actually have any variables in there because otherwise it wouldn't evaluate. So we can do this with the non-empty thing, and we can go ahead with this.
Sorry, are you saying that you couldn't prove this for open terms in your system?
You could prove it for this. You would have to have an evaluation that would evaluate open terms. Our evaluation doesn't.
I see.
You could write evaluation relations that take open terms. You'd have to say what do you do with, or maybe they just want to evaluate. Okay, so and then progress is not true for open terms. Yeah, preservation would be true. Yes, preservation would be true. So you would be able to prove it in SASyLF even. So and of course the way we're going to do all these things, we do induction. And if you look at TAPL, it says it does induction on D, and then it has a exercise, an uninteresting exercise that says, because it doesn't give a solution, which says do it on E instead. And I can assign that for homework. So we show it in D, and then they have to do it for E. So save it here, and of course, don't tell anyone about this quick fix, but go ahead for it. And we have our various things. Let's work with TAB. Actually, TABs is moderately interesting. Notice it uses U all the time because I said that was a possibility. And I don't happen to like the U's, but so I would change them back if I were to do much with this. The thing going on here is we have actually no, we can leave this. how are we going to handle the preservation case here? How do we preserve, if we're preserving the type after we evaluated a lambda abstraction? Well, it turns out they don't evaluate. I'm sorry. So the functions are values. So it turns out there's no way to evaluate that thing. And fortunately, we can do that by an empty case analysis, which can be written as, it's just syntactic sugar for an empty case analysis on E. So there's that. Okay, so now we're on this one here. And now I really am going to give these different names. I don't like this called U0 and U1. I'm going to call them T1 and T2. And that means I'm going to need to have T1 as type, and then let's come up with some other type. I'll call it T2 because that's the type of T2. As I said, I have problems with my fingers here. Let's see if I can go down.
Your muscle memory
is for a different computer. Yes, so that's fine. Okay, T2, and that's T2. It's good to save it again, make sure I haven't made an error. We're getting these warnings. Over the break, we talked with some people. It's because SASyLF by default requires you to say what substitutions are happening in a pattern match. And so I have to say that this is this where clause here. It's not needed. SASyLF doesn't need it. It's forcing it for the students so they understand that T is actually the same here. So when we're looking at the value, we know it already is an application. And of course, we'll just call this D1 and D2, very exciting names. And how do you think we'll do this? Obviously by induction, but we can't do induction. Why not? Not yet. Again, thinking about recursion, this is a function that takes how many inputs? It takes 2 inputs, these 2 here. And so if we want to do induction, we need to have 2 inputs also. If we're going to do on this one, we need T1 as a type, which we have, and we need T1 evaluates something, which we don't have. So how are we going to do that? Yeah.
So actually, this is not an answer to that.
Yeah, that's fine.
A different question. We're saying that T is equal to, so that where statement on line 65.
Yes.
This T is equal to T1, T2.
Yes.
Which we're going to prove is a type of capital T.
Yes.
And we just need that for preservation. That's like
yes.
The definition of preservation.
Yeah.
Okay, yeah.
That's right. And so if you sort of hover over this unproved, and T will say we need to show that T prime is of type T.
Because we just gave it a
and we don't, and that's going to be what T1, T2 evaluates.
Okay, yeah.
Yes.
To answer your question,
yeah.
I think, if you want to use an action on D, we have to make a case analysis on E first.
Yes.
We know all cases of E.
Absolutely, completely correct. So we need case analysis on E here. And again, I'll go ahead and be lazy here. I could say I'm doing it for the interest of time, but okay. And we have our EAP1, EAP2, and EAP apps. These are interesting ones here. So again, I don't like the name U0 here. I'm going to call it T1 prime. And then we have T1 prime. Okay, I told students that if you want to do your proofs, you want to choose names that make sense. So I don't want to go to some random variable. I want to have a variable that will make sense to me and give it a name that makes sense. If you don't do the naming right, you'll just have numbers going on, E17 and E18, and it's just going to be horrible. So you can mix up numbers and primes all you want, and you can have 2 dimensions. It usually is enough. So what is this warning about here? It's warning us that we don't have a where clause on T prime. And let's say we guess it wrong. We say where T prime is T1 prime, And it will complain that that's wrong, and it'll say, well, actually, it should be T1 prime T2. It won't fill it in for you, but it will at least tell you what you need to do. Again, this is because it was done for pedagogical reasons. So now we know that T prime is that. And so if you go down here by unproved, we'll see that we want to prove that T1 prime T2 is type T. Now what rule would be used to do that? To prove this thing here. How do we prove that T1 prime applied to T2 will have type T? What? Let's look at the, yeah, it's going to be one of those rules. You can say rule T, and then maybe we got this thing, and we have, it will show each of the rules that we have there, and TAP is the obvious one we need to use. And we'll say that when those are the two premises we need, let's go for this. We'll say, okay, now we need to know T1 has this type. And so that's going to be a, let's say, T1 prime. Oh, that's because it's showing the rule, it's not actually applied it to us. We'll call that D1 prime, and then we'll have D2, and we save it, and it not surprisingly complains that we don't have D1 prime. Another little quick fix here, and it will say D1 prime needs to be this guy. And then how are we going to get that? Yes. So that's going to be induction hypothesis on, and I spelled induction hypothesis wrong, and that helps you. You notice that it's not highlighting correctly. So on, we need two things. That's going to be D1 and E1. And so then we have that, and we save it, and we're happy. Okay, let's skip EAP2 for now. Let's look at EAP apps. This is the fun one. Okay, again, I like having good names for things, so let's call this V2. And I'm going to call this T2 here, and call this T11. And then this will go to T11. Let's see if I did that right. No, I did it wrong. So what did I do wrong? It says missing where clause. No, it's more than the where clause. Okay, where T1 is lambda x T2. Oh, did I already use T2 in this? T11 of x. Okay. And that warning is there is now it's overly strict. It's telling us that we're reusing T2. We thought that that was a fresh variable around here. And this is actually a mistake that was made in the original printing of the TOPL book. It assumed that T2 was the type of the thing here. It's not quite on this exact line, but it's a very easy mistake to make, to assume, well, of course it's going to be the variable we want, but it's not going to necessarily be that. So we have to use T2 prime instead. And then, of course, this has to be the same one. And there's probably another error here. Okay, nothing else is that we need a where clause for T prime, sorry. And T prime is what? What is the result of our evaluation? Yeah. T1 substituted with T2. Exactly right. Okay, so now we've got our where clauses. I always have the students fill in the where clauses immediately. And even if you're going to let the quick fix do all the work for you, you still need to put in where clauses and choose reasonable names. Okay, so now we have to prove that this guy here, T prime, is the right type. And what we have is we have that T2 is a value. And if we look up in our context, we also have that T2 is type T2. Now T1 is this thing with T2 prime. So it may not be the right type. How do we know this is going to be the right type? So the proper answer, which the TAPL book does have, is it does inversion of the typing relation. And it turns out we can just use inversion of rule. Which rule is being used to type T1? Actually, I shouldn't have said, so I'm going to put something here.
You're going to use inversion to get a.
I'm not going to use it, sorry. Yes, it's right, because no, we need the thing on D1, and I want to keep the proof by unproved here. Sorry, I just want to always leave this at the end. So what are we going to do? Inversion on D1, which is, this is something that's moderately useful. You can sort of collapse cases that are sort of getting in the way of your, you want to just get this case out of the way so we don't look at it. And so, I can fit it on the screen. So we have D1 has that type there. T1 has that type. And we know T1 is a lambda. So we want to invert, which rule is it that T1 is using? Anyone happen to know what it's called? Over here, you can actually open up, it's T-abs. You can sort of see, let's see, can you show me? Yeah, it will have a little teeny font. We'll show you each of the rules over here. But so that's going to be rule T-abs. And it has a hyphen in it. And what will that give us? That's a capital A, thank you. And what will it give us? What is this? What is T-abs going to give us? As people remember, if I invert this thing here using this, what is it going to give us? Remember, it had a larger context, had gamma, which gamma is the empty context right now, but it's going to have a new context, X of type, since it's this T2 here, and this T2 prime, the rule T-abs forces those together. So I'm just going to say T2 here, and then T11 of X will have type what? T, yep. So let's see what we get here. We get a little warning that says missing where clause, because this forces the thing together, and it wants you to be realized that this is the thing that forces these two things to be the same, this inversion. So now we have the fact that the body of the function has type T, and we have that the argument has type T2. So how do we get the result? In the TAPL book, I'm going to call this B11, we have a substitution lemma. So we would have something like proof by lemma substitution on D11 and D2. Let's write that lemma, okay? At this point, it turns out we wouldn't need to actually write it, but let's look at that lemma. Lemma subst is going to take, it's actually going to take a gamma with an extra argument, X of type T2, let's say. T1 of X is type T. And then we have another thing, T2 of type T2. So if we have for all, let's make this for all D1 and for all D2 exists what? What does the substitution lemma tell us with this? So we have in a context with the extra context of X is type T2, T1 of X is type T, and then we have some T2 that says has type T2. Substitution lemma says that if we, T2 should have type T. And of course, we need a context there. So I'm just going to use whatever is the outer stuff there. And I have to put, yes, I have to put something in here. Proved by unproved. And then we have a little warning because it wants you to realize that gamma is not syntax here. Because since this relation is typing relation, gamma is actually, this is a hypothetical. And at the LF level, this is actually a function. It takes this hypothesis and gives this result. So we need to say assumes gamma here. Just to make it clear that gamma is not syntax. We can't do things on syntax. Okay, so this is the statement of it. Now, at the LF level, this is a function. It takes this hypothesis, which is the variable plus the hypothesis that we said, which is the typing. So we have something which has that type, and then we'll give this result back. Now, it turns out that that LF function, all it needs is taking this as a parameter and gives us the result. So basically, we need to run the function D1 with D2 as a parameter. That's what's happening at LF. And so in SASyLF, since it's built straight on LF, we just say substitution on D1, D2. And that will do it. Because it's substituting the hypothetical with the actual thing. If you use a hypothetical judgment instead, like I have in my homework, you have to write a standard substitution limit, which is fine. You can write the standard TAPL substitution limit. But for this case here, since this thing here, the typing relation, is the one which is put into the context, that's all it needs to do the work there. So substitution gets us to that point. Okay, so that's progress. That's preservation. And we've handled all the interesting cases there. What the other one we have is progress. I keep saying that, and that is, again, you have to have an empty context.
Can I add a couple
Yes.
on that?
Yes.
So first of all, I think pedagogically this is a great approach to defining the dilemma. But you could also have done proof by substitution down in the middle of the operation here.
Yeah.
So the lemma is just
So down here, instead of saying my lemma subs, I can just say substitution. So,
the other thing that's John described this in terms of LF contexts, which is exactly what it is from a theoretical point of view.
but it's not good for the students.
But some of you probably know what an LF context is, right? Maybe not all of you. I certainly didn't before I got into this stuff. So the way I talk about it with students is that basically what gamma, what x equivalent tau in gamma means is that there's an assumption that x has this type, right? And when you substitute in, you're basically substituting in the term that has this type into the other term, right? That has the bound variable. But you're also basically, if you have a derivation that depends on a gamma that has x equivalent tau 2, what you're saying is there's this derivation, and there's a hole in the derivation that says, oh, at this place in the derivation, I'm depending on the fact that x has type tau. And when I do substitution, I'm not only substituting the value, tau 2 in for x, right, t2 in for x, I'm also substituting the entire proof that t2 has type, t, in for that hole in the proof that the other thing is well typed, right? So everywhere there's a hole in the proof that the term with the variable in it is well typed, there's a use of this assumption, and I'm just plugging in the proof for that thing everywhere, right? That's sort of how substitution. That's what substitution lemma means. So why does this work in SASyLF with this one magic strategy of equal by substitution? Well, it works because of these rules about how you construct contexts and how you use them, right? There's this pattern where you construct a context that has one variable and in the context, and then a right-hand side that tells you what you're depending on, right? It's the typing judgment, and it's the typing judgment with T as the type. And so basically, because SASyLF puts the restrictions on it, it says the only way you can use an assumption is by having this kind of rule. Then the substitution lemma is guaranteed to hold. Basically, the way SASyLF makes sure the substitution lemma holds by construction because of restrictions on the way you declare these rules.
Yeah, that is the much better way of expressing it to students, to talk about we're substituting this thing that we've demonstrated there.
Right.
And then if they start sort of pressing a little longer, either wave your hands a little more vigorously, or you say, okay, now we'll talk about LF.
Right. It all can be made rigorous. But right, it's nice. It is a legitimate proof methodology, right?
Yeah.
I think if you explain it in those terms, then people can understand, oh, there's a hole in proof, and we're substituting a piece of the proof in for that hole right when we substitute the variable into this term. So, yeah.
Yes?
The way I'm reading gamma, definitions for gamma, it looks like it's ordered. Is that intentional?
It syntactically is ordered, but in the context it's not. But whenever we write it out, it always writes out as ordered. And so if you change the order of two things, you have to say by exchange. But exchange is built in because it doesn't make any difference, actually. So there is a little bit of order because there may be, if you have types in your thing which have subtyping relation, you could depend on an earlier typing context. So the ordering is there at some level, but it's very easy to swap.
Okay, this is not in a rule. This is like kind of implicit in the.
It looks like there's always an order, and at some level you need it syntactically, but it's very easy to swap it. It's like a function, the two parameters of the function, you can always call the function with parameters in the opposite order. I mean, it means something different, but you can do it.
I guess my question is like, if you wanted to prove something that required swapping around.
Yes.
Right now, there's no rule that lets us swap.
You have to state by exchange.
Okay.
Yeah.
An exchange lets you order it lets you permute any of your things there that can be done syntactically.
Okay, that makes sense.
Yeah.
So I told a white lie earlier. I said the only things that are really built into SASyLF are by rule or by theorem, case analysis, and by induction hypothesis, or by something you already know, right? But in fact, there's three more: substitution, which you just saw, weakening, and exchange.
But weakening just lets you add more things to the code.
Okay, and that all makes sense. Okay.
Yeah.
So there are slightly, actually, it's only like one small step beyond this where you start to get weakening and exchange.
If you actually had to, if you wanted to prove substitution all the way through inductively, you would need weakening.
Yes, there you go. Yeah, which
makes
sense.
Usually weakening and exchange also comes with cut rules, so you get cut rules.
There's a proof of cut elimination in the SASyLF examples you can see there. And that actually demonstrates some very interesting things with induction, because cut elimination can't do simple induction, you have to use lexicographic induction. Though it turns out to look pretty normal in SASyLF. Okay, I want to leave 15 minutes at the end actually, no, you have something more to do also after this, is that right?
No, it's just
so I wanted to look a little more at, so a little bit more, let's look at progress for a little bit so you can see ORs. And then we will break for some more questions. So progress is what? I have to give a name for this thing. It's not happy without a name. Yeah. Yep. So T is a value or exactly. So you have something like this. So OR is built in and it's fairly sugary. It's basically built in by adding new judgments. it makes a judgment that ORs these two things together automatically for you. And this is, sorry, I'm going to go into a little bit of a rabbit hole here. Notice that this has T prime in it. And T prime is implicitly existentially qualified. So it means that we want to say it exists. But you need it for this one here too, because the theorem says we have a T prime such that this combined judgment is true. But that is sort of bizarre that you need a T prime to say T is a value. So what SASyLF does is assumes it's always possible to create syntax. So if you come up with your judgment that it's a value, you don't also need to say, oh, by the way, I have some other term here, T prime, which we're not even using anywhere. Well, make it unit or something. So SASyLF realized I can do that on your own, but that means that SASyLF assumes it can always create syntax, which means your syntax has to be productive. So if you have an unproductive syntax, that's an error in SASyLF, because otherwise it can be unsound. That's just one of the sort of the weird little corners of SASyLF that had to be fixed to stop students from proving things that are proving contradictions. So,
thank you.
Yeah. And let's see how far we get on this. Okay, so this is the progress here, and no surprise, we are going to use induction on D, and we have case analysis on D, which is just a slow way of just saying proof by induction on D. So this is also going to show that proof here is just actually shorthand for saying the thing you're trying to prove. Whatever you're trying to prove, in the original SASyLF, you would have to write it out. You'd have to say here, I'm going to prove that T is a value or T goes to T prime like this. And proof is a way of just writing that shorter, so you don't have to constantly mention it. That's all. The keyword proof just means whatever I'm trying to prove. The quote Eric, whatever it is that we're supposed to do, we're doing. That turns out to be totally obvious until you get into ORs, and that becomes moderately interesting. Let's go ahead and get our quick fix here. It sort of sounds like I'm getting some sort of drug hit.
I see it. It's okay.
Yeah, exactly. I don't need my quick fix. Okay, how do we prove the abstraction case? No, it's not my induction. I'm sorry. Functions are values, exactly right. So we need to prove, let's see here, we need to prove that either this thing is a value or it evaluates. Now, clearly it's a value. I mean, that's on the t-shirt now. So we can say by, go away, by rule val fn. And then SASyLF is going to complain. And it says this rule cannot produce an instance of OR. So value is not equal to OR, value, or small step semantics. And so this is like, but it's just showing because the proof keyword, I'm claiming that I'm proving an OR with the value. But it does not prove it. It proves. So this is this case where you can't just constantly say proof. You have to say what you're actually proving. Proving T1 is a value. T is a value, sorry. And then it's okay. And there's actually an implicit thing going on here that when it checks the last statement of your body, it checks that you're actually proving what you need to prove. And we prove this. And what we're trying to prove is this. And it has an implicit coercion in the body to allow that OR to happen. So I don't necessarily say this makes SASyLF look good, but it just sort of shows some sort of problems you can get into with, okay, now we're going to do some things up here. We have D1. This is
Just to add to
T1.
that point,
Yes.
I like is supported for OR that John added. I think it makes things nicer in some ways, but it also it's another construct you have to teach. So
Yep.
So when I give an assignment based on this as well, and I actually just define a rule, steps or value. I define a judgment, steps or value, and there's two cases.
Yep.
T is a value, so T steps or value is either T is a value or T steps to T prime.
And that works just fine too.
It works just fine.
Yep.
It's a little bit simpler, a little bit more explicit, but you got to define this extra judgment.
And then they know how to do case analysis, and you have to follow rules.
Right. So that.
And there you would have another step to then explicitly put it into.
You then have to explicitly construct at the end.
Yeah.
T steps are value by rule. T steps are value dash value. Right. So yeah, it keeps things a little more conceptually simple, but it's one more piece of overhead. So pick a count which you want to teach.
And before you decide that, you have to look to see how we're going to use this thing, because it's a pain that we end up with pain in the inductive hypothesis too. So obviously here in TAP, we're going to want to do the induction hypothesis on these guys. So what happens if we can run the induction hypothesis on either D1 or D2? What will D1 give us? We run the induction hypothesis on this guy. What are we going to get?
It's a value.
It's a value or an expression. Or a value. And the same thing here. Yeah, this is a value or a value. Let's just try one of them. So we have, I'll call OR1. We'll get D1 is a value, or T1 evaluates T1 prime by induction hypothesis on D1. Okay. And now what do we do?
We have to do a case analysis on the OR.
Yeah, because how are we going to know which one we're going to do? And at this point, we're not going to necessarily we know that it's not going to be a value. How do we know that T is not a value? T is this thing here. It's not a value. So there's no point in trying to continue to prove an OR. I'll find, to avoid this problem here, the lower problem happening over and over again, we're going to say, actually, we're going to prove that T goes to T prime. And then that means inside of here, we're going to do, say, case analysis on O1 and case analysis. This means that we are inside here only need to prove it at evaluates. We're not going to have an OR anymore. And then, of course, we get our quick fix. Okay. Now, ORs have a very special sort of case analysis. So you have a case OR of the two possibilities. So it's a rather ugly syntax, but it was able to fit, and it used keywords in a way that sort of made sense in some level. So let's see, I lost my colon there. So now the thing we're trying to prove here, proof by improved, is no longer the OR, but it's just the evaluation. Show that T1, T2 evaluates T prime. What if T1 evaluates T1 prime? What do we do then? If down here,
Did I hear someone say just keep going?
T1 evaluates T1 prime, we have to show T1, T2 evaluates. Yeah. Yeah, it's the EAP1. So, yeah. So and it will tell you what you need here. So I'm sorry for the small font. The EAP1 requires that T1 goes to T1 prime. That's just copied from the rule. It's not our current T1, but it turns out since I named my variables rather than U0 and U1, it's so I'm going to choose EF1 on, and then it'll give a little thing, say, hey, we need to evaluate T1, and that, of course, is E1, and we are happy. Yes?
How often do you find students getting confused by the number of different T1s floating around in a different group?
They get confused. Yeah. So the, especially when T1 isn't T1. If T1 is T1, no one realizes there's a problem. It's like, oh, that's great. But yes, when it's, you see the rule and then you need to apply the rule. So that's why I really need students to understand substitution and unification. So even though SASyLF is helping them, you need to understand how to substitute things and how to get how to take the rule and instantiate fresh variables, how to do unification, and that is one of the hard things about this.
In fairness, this is one of the hard things about any proof.
Yeah.
Right? You can make the same mistake on paper, and students often do.
Yes.
And they don't even know, they don't even sometimes realize that they made a mistake, right? So I don't think it's actually an artifact of the tool, it's actually
Yeah, it's not,
tool.
yeah.
It helps you with, because
yes.
the tool tells you when you got it wrong.
Yes.
When you're using tools like this to, like, you know, for a class, do you ever find that, like, having the student do it by hand can be helpful? And do you ever have them, like, do it both in it and by hand one way or the other?
So for this, they have to do it by hand, but in terms of like the case analysis, that's why I don't tell them about the quick fix for case analysis until about the 4th or 5th week of class, because I want them to write out the cases. And writing out the cases requires them to kind of fresh instantiation of the rule, unify the conclusion of the rule with the thing we're doing case analysis, and then to resubstitute through. It's actually really a complicated process.
Yeah.
And after they've done that for a few weeks, I feel they've learned it. And I say, oh, by the way, SASyLF will do it for you. But I'll still force them to do the where process. Yes.
Is there enough information in the back end, or is like 12 smart enough to be able to provide hints to the student? So if they may like go, what T1 are we talking about? Or
So let's say you did the wrong one, or something. Let's say, if you do the wrong thing, it's the SASyLF is all built into Java. I mean, it's all written, it implements all its own stuff. So if I give the wrong type here or something, give something like that, then you get an error that it's the premise is wrong. So, and if you do a case analysis of the wrong variable, like I did earlier one where I had the wrong variable, if I tried to say here, go away, sorry, sticky keys. If I do something like that, you get an error and we'll say, hey, this case is bad because you are, I'll read it out. Case is overly strict, perhaps replace the following with a fresh variable capital T. So it's saying somehow capital T is being used where you need a fresh variable. It doesn't say which one it is, but it turns out this is the one that should be a different variable. So,
it sounds like you're not interested in like proof repair, like hints through proof repair or anything like that.
so we have, that is a hint of proof repair, but so that's the level we do.
Yeah, we could be more specific. Well,
yeah,
we could be more specific.
It's hard to tell because when the unification fails, it could fail for a lot of very strange reasons. And I'm actually impressed at how many ways that you came up with useful. It tries, what if I try this and tries that and sees if we can it tries very hard to give useful error messages for unification, which I think is good because unification can fail in a lot of very strange ways. At some point it just gives up. It's doing higher order unification, which is undecidable. So sometimes it just says, I can't handle it. So, yeah. Yes.
So you said that you really need students to understand substitution unification
Yes.
going into this. Are you teaching this before you're introducing the tool? And so, like, in how much detail are you introducing unification?
So I in the repository here, I have this HTML thing, which is a web page that's going to, okay, it doesn't work on your thing. That's okay.
I can open it in my browser if you like.
That's okay. So it's yeah, that's okay. So, but the
you keep talking.
I don't know if it's going to work. But the I have this little thing to have to practice unification just as you want terms. And they're supposed to have it in their prerequisite course, but the prerequisite course doesn't go very deep in unification. And
So is the prerequisite course like a functional programming course, or?
it's a sort of a general programming language survey course that teaches you a little ML, a little JavaScript, and talks about context-free grammars, which is really important, and a little bit about evaluation and what a perception is and things like that. It's a fairly shallow little course, but it does really get them into, they understand functional programming a whole lot better. Like, it gets them to ML, and they only do Java, at least in my university. And so the thinking in ML is a big, mighty experience for them. So that's really helpful. Functional programming isn't scared of them, and they run on constant grammars. And unification, while it's sort of substitution, sort of obvious at some level, and then I just want to think about it a little longer. So it gives a sort of definition, thank you, the definition of various things, which is very boring. And then at the end, it has some exercises. And at the exercises, at any point, they can go back and look at the definitions again, because they probably skipped through the definitions. So you're like, here, okay, I'm supposed to substitute X with D inside of that input. Well, what does that mean? I don't understand. Maybe I need a hint. Maybe it's going to not tell me anything. So there's the hint. Replace X with D. So A of B. Okay, good. And then you say submit, and it says, okay, you got it right. You continue, and it does something harder. So it has 10 exercises with some mild hints that get harder and harder as they go along. It turns out substitution can get pretty profound with these things. So okay. So I think we've actually seen enough to sort of see how the flavor of using ORs and do case analysis on them. So I think I've sort of covered enough of what we were going to do for that section. The exercise has us do some more things. Add the let, and then update the progress and preservation proofs for let. It's basically just your trying.
Yeah, so exercise 3 here has a complete version of this proof that John was just going through, and yeah, so you can uncomment the rule, and then
suddenly your proofs all fail.
you can like do a case of the proof yourself. So it's not rocket science, but it's like a variation of application of abstraction and application, I guess. So.
Now, if you go back to the slides.
Yeah.
So now that I've sort of shown sort of dirty secrets on this thing, this is sort of the slide I have on it. So the idea of SASyLF, when a variable goes into context, is always accompanied by an assumption of a relation. And which relation that is done implicitly by using one of those special rules. And in the case of the example there was the typing relation had that special rules that meant that typing goes into the context with a variable. So here, the student gamma, that's not syntax. This one here, this is a special kind of rule, shows that T-var is the one that says what assumption goes into the context. And it's a typing assumption. And then I was going to just go a little more. This is the substitution we talked about. And then I did the live proving. A lot of my systems, I don't want them to do that. I want them to actually have a special assumption that something's a variable. If people use 12, this is a common thing to do in blocks. I don't know if anyone has done 12. 12 is very strange, and, but sorry. It was my first real proof system I used because it's not about programming. But the idea is that we have this judgment that's never true for any syntax. It's only true for variables. And that means if you want a rule that says, I evaluate variables in this way, or I don't evaluate variables in this way, you can actually say whether something's a variable or not. Because otherwise, there's no way of saying something's a variable. But the disadvantage is that since this thing is only hypothetical, there's no way to ever substitute. Because you can only substitute one variable with another. There's no proof of anything being a variable because nothing is a variable. None of the syntax is a variable. Only variables are variable, and variables were just hypotheticals. So then you just prove your substitution limit in the normal TOPL way. And the example, our repo has something called SumProd, which is looking at sum types and product types, adding them to the simply type line of calculus, and it uses that way of doing it. That was what I wanted to say about that.
So I guess the point of this is it's an alternative.
Yeah.
If you want people to prove substitution in the normal way in your class, you can make them have to do that if you just use this.
And if your relations need to talk about whether something's a variable or not.
Okay.
It turns out otherwise, you can only have one rule that mentions variables. If you use it up on typing, you can't use it for anything else.
Right. Okay. So there's more theorems you can prove if you use this trick.
Yeah.
Okay. Nice.
And
Let's prove more theorems with SASyLF.
yeah. So as a trade-off, when we do assumes, we can use context in a natural way, but you cannot case analyze contexts because they're not actually there. Getting both, I think, would be possible if we had variable arity LF, and I've tried to prove that, and I have the syntax and I have some semantics, but I've never been able to prove that it's sample. So we don't have that in SASyLF. And then we also need to have higher order variable arity unification. There's no, who knows if that's even possible. So even semi-algorithm. So that's just sort of up in the air. I spent a whole year trying to figure this out, and I never was able to prove soundness. I have had some interesting things, but
sounds like a PhD thesis.
It'd be cruel for me to give that for to a PhD thesis.
Maybe a dangerous one.
Yes, oh, that's a wonderful problem. And not well as known, but it could be a useful PhD.
I take back my suggestion.
A PhD thesis could prove it, or prove it's unsound, or something, or or sort of show some more possibilities. And I think then we're now to the discussion.
Yeah. Okay. So this is just, I guess, wrapping things up. Well, I'll go through these quickly, but just a little bit of how we use it. So this is my course, undergraduate programming language course. It's a mixture of theory and of actually building a compiler. So you see how languages are defined and then how you implement them. So then half of the assignments focus on theory. We put all those in the repository that you have. So it's like exercise 1, extension of exercise 1, introduction to rigorous proofs, extension of exercise 2, modeling of dynamics to lambda calculus, and proving small step, big step are the same. Modeling statics of lambda calculus and extending them and showing that the proof continues to go through, and then an optimization proof, constant propagation. I didn't finish my sentence here, but basically, students like knowing that the homework is correct when they have it correct.
They love that. They love the little green check mark.
Yeah. It's very motivational, right? And it gets them to actually engage with the proof. I feel like we have very productive office hours because they come in with SASyLF. And sometimes it is like, oh, here's an issue with the tool, but usually it gets back to, oh, here are some interesting problems with the way they formulated the proof. And so I feel like it ends up being like the tool, it causes some frustrations, but those frustrations push them in the direction of learning something. So that's, obviously this is my qualitative experience, but I think it's pretty positive. There are some minor issues with the tool. Make sure you do the assignment first to make sure you kind of hit those and can steer students around them. But with a little prep of the assignment and students, you can smooth these over pretty well. There are a couple of improvements we want to make. Actually, one of those is there's a better algorithm for unification than the one we originally put in the tool now. So that's on the list. But again, we're being able to do a lot in these courses, even despite those issues. So this is John's course.
Real fast. As I said, I use TAPL for my textbook. We cover most of TAPL up to 27, which is F sub. We're able to have a homework every week, in which 1/3 of the homework is doing the proofs. Undergraduates only have 2 parts of the 3. They need to do the proof and then do, it's a little shorter. The course is elective. I don't get a lot of students taking it, but it is on the topic for the qualifying exam for PhD students, so I get a few people. UWM students, usually the people coming in have never used a proof of system before. When I taught at Northeastern, I had people who'd done comp before. And for them, SASyLF was just, oh, this is so nice. Who never caught, whereas my other students are like, this is a real struggle. And I want to tell them, no, comp is worse. But they anyway, so back to you.
Yeah. Well, this is a little bit of you too, but yeah. So what can be proved? POPL'23. probably some of the other POPL marks, but we haven't done all of them. So this is your experience, John, with most of the main results in TAPL through chapter 30. The main difference is logical relations, cut elimination, and this is your paper, right? Or no, you duplicated a result in a recent
I
paper.
duplicated a paper from isorecursive subtyping that offers me speaking POPL on Wednesday with a new extension.
So yeah, and then almost the soundness of LF, but one unproved. So some work we still need to do, I guess. SASyLF is designed to be easy to pick up. The mechanisms it uses are kind of taken from paper proofs and like teaching tradition. But I think what's interesting is, under the hood, it's common mechanisms with the proof assistance, right? SASyLF is really a functional programming under the hood. And I have a lecture at the end of my class where I talk about the Curry-Howard isomorphism, and I show that, oh, look, here is factorial programmed in SASyLF. So it's pretty fun. Actually, no, I think it's Fibonacci because it's addition, but whatever. So I think what are the differences, right? Tactics. Obviously that's a great productivity booster for people who are experienced. I think what's nice is SASyLF kind of helps people through those earlier steps, and it could be looked as a preparation for tactic-based proof assistance.
I had a student who, after doing SASyLF, did Isabel for doing type safety of the new JavaScript WebAssembly.
Oh, WASM, yeah. Great. So that's all we have. Any further discussion or questions? Yeah.
It's really from the perspective of y'all designing a programming language, you have an interesting set of users.
Yeah.
And that you have it's cohort based, and after they write the final, they will probably not think about it so much. So there's kind of an interesting opportunity to almost A/B test new structural changes to the language. So you don't have to worry about backwards compatibility, where 2008 cohort is going to understand this thing. Is that something you think about, thinking about it, or have you actually done that? In this, in the winter quarter, we're going to remove some particular language features, try and play with these just to see what works better.
No, we haven't done that, but I have done the sloppy version, which is I add features to SASyLF if I want to, and not worry about the existing code base. Yes.
Yeah, no, it'd be interesting to do a formal study, and we haven't done that to date. Yeah, I mean, we could. It would be cool to compare outcomes of teaching without the tool versus teaching with the tool. It might be you could also compare teaching with SASyLF to teaching with Cocker-Agda or something. Yeah. I think that might be harder to do in a kind of fair way because for those tools, I feel like there's probably a lot different content that you would. It would just change a lot of the way you would teach the class because you'd have to spend more time on the tool. But
it used to be that for the final exam, I gave an entire paper proof that we're supposed to look at for finding errors. I stopped doing that, but that was in order to, one of your initial things was, do people do better on paper proofs if they've had SASyLF? And I didn't do an experiment, but I was doing that. So
yeah, no, it's a great question.
I have two questions. One's a meta question. So let's start with a non-meta question, which so does SASyLF have functions? For example, could I define an evaluator, basically the evaluator as a function?
No.
Because something that's really uncomfortable when you're defining the big semantics is when you just de-unrule, the proof will go through, but your interpreter is wrong. And having type check for you didn't omit any cases of rules.
You can do a totality proof to do that. That's the way you check adequacy of that.
But then you have to do that entire.
You have to write a totality proof.
Okay.
Yeah.
Okay.
Yeah. You can also test it by one of the things we do when we give assignments that ask students to model something we give them a proof of it's like one of the simplest proofs is just constructed derivation, right? Because the constructed derivation that this evaluates to that, and then if they've defined the rule in the wrong way, it won't work.
Yeah, we have it. If you do case analysis wrong, you don't put the things in, you can't actually prove type safety. We can't prove the type of something. So sort of an adequacy lemma that says, okay, now show you can prove the type of this. And yeah.
Except if you have something like approximation, and you duplicate the rules, and then you left out one of those duplicate rules where you propagate an error and you fix them.
Yeah, the fully doing adequacy is not possible. But you can do a lot towards that with lemmas or requiring people to prove totality.
Test cases, you know.
Yeah, test cases. Actually, it's like test cases.
Right. Yeah. Literally, we give them test cases. You know, you have to prove this with your semantic.
Just like with a regular test case, they can work around it with really horrible code. But
I suppose they could. Yeah. But I guess
case.
it makes it much less likely that they'll kind of screw up in that way, because you have to screw up in exactly the right way to get around that. So I think in practice it helps, but there's no guarantees, right? You can always do it wrong if you do it wrong in a complicated enough way.
So I guess, well, just to wrap it up, is it a design decision to not include functions, or is that just from LF or?
Oh, well, I mean, I think it's a design decision, but it's driven by the goals and pedagogy of SASyLF.
The LF doesn't really have functions. LF has functions, but they're really, 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 really limited, which is why substitution works.
Right.
So, because substitution, those are functions, but they can't do case analysis on that. I'm going to move to you first, and yeah.
So, yeah, it seems, pretty compelling that, like you said, you don't have to spend a while teaching the tool, whereas if you taught someone copyright or something like that, you could waste, a week, 2 weeks at least to get people to do something. Not waste, that's the
yes.
But because it's like more useful for later. But
yeah.
But I could imagine you drop this tool in for like a lecture or two of class. Obviously the two of you are like dedicated to the tool, and so it makes sense to like use it for more of that. But where would you deploy this in sort of like a grad level or talented undergrad level, class? Like which other places could you do?
Well, my talent course, I do it. I've had undergraduates do a thesis on, I had them prove the correctness of ABL tree balancing.
But they've been doing a lot more of it through the semester, right?
And that was someone who hadn't taken my course. And so he had to learn SASyLF at the same time he was modeling. He'd already taken a course with AVLs in there, just proving that it was correct. So it's not as much of you can do it fast.
Yeah.
Especially with TAPL, because TAPL, the syntax is modeled after TAPL. So it just sort of looks like, you just sort of pretend it's the same thing. And then, of course, they run into things and you explain to them, oh, actually, blah, 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 blah. But it's sort of by bits and pieces. And you and then. So.
Yeah, my question goes in the direction of tactics. Do you have any experience how students adapt to tactics in other proof systems, and the other way around, if you thought of adding tactics to your system? Would it be possible?
We've decided not to add tactics.
Yeah,
in my opinion, tactics solve easier problems and leave the harder problems for intelligent proofers.
I think, from my point of view, it's often for beginners difficult to understand all these tactics if you haven't done proofs yourself. I think your system is like perfect for this case because you start by doing proofs step by step. I mean, you have to be very explicit in every step, and I think that's a good start. But like you said, in the end, it's very tedious sometimes for bigger proofs. And I think it may be an option. I don't know if it's feasible.
My student who went to Isabel discovered the sledgehammer thing, and I'm just doing
Just
take the sledgehammer, bang, bang, so they find, but it doesn't work. It doesn't work, then like, what do you do? So
I have a slightly different answer. Okay. I mean, I think I philosophically agree largely with this point. I was actually just talking to Talia Ringer, who was here in the first half over at lunch, and she's interested in a graduated approach where you start with the term language, which might be, I would advocate for it to be something like SASyLF, right? To introduce people to proof assistance, and then layer a tactic on top of it. So I think as a language levels approach, that could be very effective. I probably wouldn't apply it until the second half of a fairly advanced course at the earliest, but I think you could apply it. One thing I would say is what I would do in taking advantage of SASyLF is, in COC, well, I'm not a COC expert, but my understanding is you apply the application of the tactics is entirely internal, and it doesn't show you what comes out of the tactics. And if it did, you wouldn't understand it.
You can get it.
Okay.
You can get into it, and experienced COC users can read.
Okay, great. Yeah. So, I would definitely do that with SASyLF, and I think there might be some additional advantages in that the fact that the thing that you get out of the tactic is, actually a little proof that looks a lot like that someone could read without intimate knowledge of what tactics are, or indeed anything much more than you would see with paper proofs. So I think that could be an advantage over something like COC, where even if you do get that internal thing, it's still in a language that's.
You have to be an expert to really understand it. Like, beginner would never look at that, or shouldn't ever look at that.
There's kind of a spectrum, at least Lean, there's an automation tactic that's being presented tomorrow, incidentally.
Excellent. Okay.
That has a mode where you invoke it with lemmas that you kind of whitelisted, and it will solve your goal, or you add a question mark at the end, and it will print out a short tactic script that you can put in place of it. This tactic script in this case is similar to SASyLF.
Yeah. Okay.
So,
did you have a question after that?
Small didactic question. So there's the first one. We are thinking about to have some pen and paper proofs and the proofs you went common language used. We have more transfer between them because you said you don't use pen and paper exam at the end, but for the exercises, is there a kind of balance, or only do the exercises in the
Oh, well, so I do actually have them write paper proofs on exams. And my experience has been, so you were doing a slightly different thing before, I think, where you asked them to find a problem.
Yeah.
So I actually asked them to write a proof on the exam without the benefit of the tool. I notice some effects of the tool, like they tend to use syntax that is very closely related to the tool, whereas, of course, in a class that didn't use the tool, it might be varied a little bit more. I'll say I don't have a point of comparison because I haven't done the experiment of teaching a class with the tool and without, or maybe half students with and half without. Would have to think about how to do that ethically. But qualitatively, the students are able to prove things on paper. They make mistakes. It's not always right, but people who aren't taught with SASyLF also make mistakes. So I feel like what I don't get, which is interesting to me, is it seems like it's the kind of mistakes where people leave out a case or forget the difference between inversion and assumption, or between inversion or by rule or something. But it doesn't feel like someone is floundering and they just totally don't understand proofs. So I feel like the concept of a proof has gotten through to them, and they're not just like they haven't been proving by Brownian motion the whole time, right? So I find that comforting, but I'd like to get I'd like to get more rigorous data on this. I think it would be great to do from an educational standpoint.
So one thing that I didn't see in here explicitly, but I saw it implicitly in a couple places, was the notion of a derivation or proof tree.
Yeah.
Right, you have these rules running around, and it does a really great job of getting you to do case analysis over the rules, and that's something that getting students to do in a consistent manner is really important. One thing I found is sometimes students have a hard time conceptualizing is the proof tree as a whole, developing these rules, and how the induction manifests in that. Do you have a way of displaying that here and showing that, or manipulating those other than through this case analysis?
Yeah, I don't right now. I did have a student build an experimental tool that would take SASyLF rules and and allow them to construct a proof tree. And I think that would actually be it'd be great to have that as kind of an alternative view of a step-by-step proof. It's just something we haven't done, and takes a certain amount of like graphics programming and so on.
I do it on the board, but because it's important.
Yeah. No, I think in terms of like enhancing the student experience beyond just what like rubbing out the rough edges of the tool as it is, that would be maybe the number one kind of new thing in terms of the user experience that would be nice to add to something like this. Yeah. But don't have it right now. Yeah, okay. Yes.
Is there explosion in this module system, and can you prove explosion in this module system?
Explosion?
Like principle of explosion, like from contradiction, you can prove anything?
Oh.
It's very easy.
Yes.
Just say if you have contradiction, you can prove anything from it.
Oh, okay.
It's very easy because you just do case analysis on it and.
Okay.
There's no cases. Yeah. Yeah.
So my main question was about, so you mentioned that the tool tries really hard to be good error messages. So what kinds of techniques went into engineering that? I'm curious about that.
The main thing is looking at let's say a typical thing is that something doesn't match in unification. That's sort of the classic thing. So
unification
the
failed.
way the unification failed, it tries, if I give different parameters or I leave them out, just put variables in instead, do I get a different error message? That sort of thing. It has about 4 different ways of looking at at least the way unification might fail. That's one of the main ones. The other ones we just tried it, since it's not translated to something else, that allows us to do everything with the surface syntax.
These heuristics, they come from the literature, is this based on your experience?
It's whoever wrote that. I don't know who did that.
Did I write that?
It's either you or whoever did that original thing. Trying to come up.
It's lost in the mists of time.
Yeah.
Yeah. We should go back and like do some archaeology. Yeah, it's not even like it was. SASyLF was developed before GitHub, so I think even the history of construction of it
doesn't go back that far.
It's in a different repository that preceded the current one. So. Yeah, we have to. But yeah, it would be nice to go back and like figure that out. And there's some places where we do better. So I think there's more work that could be done. Yeah.
Okay, thank you everyone for coming. I think we're over a little bit, but
Yes.
I appreciate the interaction and it's a lot of fun. So.
Yeah. And if you want to use SASyLF, please if there's any way we can be helpful, reach out.
I'm happy to send anything I have.
Thanks.